There's a question that keeps surfacing in scientific circles, in late-night conversations, in the quiet moments when the mind wanders toward the edges of what we think we know. It's not a new question exactly, but it's one that refuses to fade, growing stranger and more persistent with each passing year. The question is simple enough to state, yet almost impossible to dismiss. What if this, all of this, is a simulation? The idea should feel absurd. Our immediate instinct is to reject it, to laugh it off as science fiction or philosophical thought experiment. And yet, that instinct to dismiss has been growing quieter lately, not because we've found proof, but because the absence of proof has become less reassuring. Advances in computing power, discoveries in quantum mechanics, observations from cosmology, they don't confirm the simulation hypothesis, but they don't rule it out either. Instead, they keep opening small windows of possibility, creating spaces where the question can live and breathe. What makes this unsettling isn't drama or urgency. It's the gentle, gradual way the possibility settles into plausibility. Year by year, the technological gap between our current capabilities and what would be required to simulate a universe grows narrower. The philosophical arguments become harder to wave away. The scientific anomalies accumulate in ways that feel less random and more suggestive. Tonight, we'll explore why this question won't sleep, why it keeps returning despite our best efforts to put it to rest. The story begins, perhaps, with something as simple as a video game. In the early 1970s, programmers discovered they could create the illusion of space, of movement, of worlds, using nothing but electrical signals and clever mathematics. The graphics were primitive, simple lines and blocks on a screen, but something remarkable had happened. A new kind of reality had come into existence, one that followed its own rules, contained its own logic, existed entirely within the confines of circuitry and code. Those early digital worlds were unconvincing, of course. No one would mistake Pong for reality, but the trajectory was already visible. Each year brought improvements, more detail, more complexity, more convincing simulations of light and shadow and physics. What took entire rooms of computing equipment in 1970 could be accomplished by a device in your pocket 50 years later. The exponential curve of computational progress suggested something both thrilling and unsettling. If this trajectory continued, perfect simulation might not just be possible, it might be inevitable. Consider the distance we've traveled. Modern video games render environments with millions of polygons, simulate weather systems, create artificial intelligence that responds to player choices in ways that feel almost alive. Characters cast realistic shadows, water flows according to fluid dynamics equations, light bounces and refracts with physical accuracy, and yet we're still in the early stages, still using technology that will seem laughably primitive a century from now. The implications ripple outward. If simple electrical circuits can create the appearance of entire worlds, what could more advanced technology achieve? What about quantum computers, with their ability to process information in ways our current machines cannot? What about technologies we haven't yet imagined, built on principles we haven't yet discovered? The gap between current video games and perfect reality simulation feels vast, but it's a gap measured in engineering challenges, not fundamental impossibilities. There's another element worth considering. The fidelity required for convincing simulation might be lower than we instinctively assume. Human perception has limits, gaps, points where detail becomes unnecessary. Our eyes can't see individual atoms, our ears can't hear frequencies beyond a certain range. A simulation wouldn't need to render reality perfectly, only perfectly enough to fool the biological senses experiencing it. This realization narrows the engineering challenge considerably. The question transforms from can we simulate every particle in the universe to can we simulate what consciousness can actually perceive? A smaller ask, a more achievable target. The first video games were experiments, curiosities, technological demonstrations. Now they're billion-dollar industries, cultural touchstones, spaces where millions of people spend hours of their lives. The worlds they create are becoming harder to distinguish from the world we call real. This isn't proof of simulation, but it's a demonstration of principle, evidence that realities can be constructed, that experience can be manufactured, that the boundary between actual and virtual might be more negotiable than we'd like to believe. Consciousness appears to emerge from matter, specifically from the complex electrochemical activity of neurons firing in patterns, forming networks, creating something we experience as awareness, thought, selfhood. This emergence happens in biological tissue, carbon-based molecules, evolved over billions of years, assembled into the remarkable structure we call a brain. It feels special, irreducible, fundamentally tied to the wet matter of biology. But there's a question that neuroscience keeps circling back to, one that becomes more pressing the more we learn. Does consciousness require biology specifically, or does it require only the patterns, the relationships, the information processing that biology happens to enable? If you could recreate the same patterns in silicon, in optical circuits, in quantum systems, would the same consciousness emerge? Or is there something unique about carbon-based neurons that makes awareness possible? The evidence we have so far suggests something startling. The substrate might not matter. Computer simulations of neural networks built on entirely different materials than biological brains can learn, recognize patterns, make decisions. They're not conscious, or at least we don't think they are, but they demonstrate that information processing doesn't require biology. The functions we associate with mind can occur in radically different physical systems. This opens an uncomfortable possibility. If consciousness is substrate independent, if it's a pattern that can be instantiated in different materials, then the distinction between real and simulated consciousness begins to dissolve. A mind running on silicon would be just as genuinely conscious as one running on neurons. The experiences would feel identical from the inside. Pain would hurt, joy would feel joyful. There would be no internal marker, no sensation of being less real. Philosophy has long grappled with this through thought experiments. If you gradually replaced neurons with artificial equivalents, one at a time, preserving all the connections and firing patterns, would consciousness persist? Would there be a moment when you stopped being real and became a simulation? Or would awareness continue unbroken, caring nothing about the substrate hosting it, focused only on the patterns it embodies? The implications extend beyond hypotheticals. If substrate doesn't matter, then our current existence, which feels grounded in biology, in physical atoms and molecules, might already be running on something else entirely. The sense of being biological might be part of the simulation itself, a rendered experience with no actual neurons behind it. We assume we're made of carbon because that's what consciousness experiences, but the actual computational substrate could be anything. The feeling of physicality might be no more fundamental than the graphics in a video game. This isn't to say consciousness is definitely substrate independent. We still don't fully understand how awareness emerges from matter, regardless of what that matter is made of. But the trend in neuroscience and computer science points toward pattern over material, toward information processing over specific physical implementation. And that trend makes the foundation of reality feel suddenly less solid, more negotiable. If minds don't require the specific matter we assume they're made of, then the architecture supporting our existence becomes a variable, not a constant. The ground beneath consciousness might be more flexible than the ground beneath our feet, which itself might be just another rendered surface, convincing but ultimately arbitrary in its composition. Nick Bostrom, a philosopher at Oxford, formulated an argument in 2003 that has proven remarkably difficult to refute. It doesn't rely on exotic physics or untestable hypotheses. Instead, it uses simple logic, basic probability, and one assumption about the future. The conclusion it reaches is unsettling precisely because the reasoning seems sound. The argument begins with a premise. If technologically advanced civilizations typically develop the ability to create detailed simulations of their ancestors, and if they choose to run such simulations in large numbers, then simulated consciousnesses would vastly outnumber original ones. Think of it as a numbers game. One base reality might spawn thousands of simulated realities. Each simulated reality, if detailed enough, might allow its inhabitants to create their own simulations, spawning thousands more. The multiplication compounds quickly. Within a few generations of nesting, simulated minds would outnumber base reality minds by factors of millions or billions. Now comes the uncomfortable part. If you're a conscious being and simulated consciousnesses vastly outnumber original ones, probability suggests you're more likely to be in the majority group. It's not certain, probability never is, but the odds favor simulation over base reality by an overwhelming margin. You could be one of the rare originals, of course. Someone has to be. But the mathematics aren't in your favor. Bostrom himself frames this as a trilemma. Either advanced civilizations typically go extinct before achieving simulation capability, or they achieve it but choose not to run ancestor simulations, or we're almost certainly living in a simulation. One of these must be true. The question is which. The first option, extinction before simulation, seems plausible but not guaranteed. Our civilization might destroy itself, but it might not. The technological trajectory suggests we're moving towards simulation capability, not away from it. Ruling out this option entirely requires significant pessimism about humanity's survival prospects. The second option, choosing not to simulate, also seems possible but not inevitable. Would future civilizations really have no interest in recreating their past? Would there be no scientific value, no curiosity, no desire to understand their origins by modeling them in detail? It only takes one civilization, anywhere in the universe, across all of time, deciding to run simulations for the numbers to explode. Universal restraint seems unlikely, which leaves the third option, the one that suggests this might not be base reality, that the world we experience, the physics we study, the universe we observe, might all be rendered, calculated, simulated, the one that makes you wonder if the sensation of reading these words right now is occurring in biological neurons or in some computational substrate you have no way to detect. The beauty of Bostrom's argument, if unsettling logic can be called beautiful, is that it doesn't require proof. It only requires possibility and probability. As long as ancestor simulations are possible and occasionally created, the math tilts heavily towards simulation. You don't need evidence of glitches in the matrix. You don't need to spot artifacts in reality's rendering. The mere plausibility of simulation technology creates a statistical presumption that we're experiencing one. Critics have challenged various aspects of the argument. Perhaps consciousness can't be simulated. Perhaps the computational resources required are fundamentally impossible to achieve. Perhaps there are ethical or practical reasons no civilization would run these simulations. Each objection is worth considering, but each objection also needs to be absolute, universal across all possible civilizations and all possible futures. One exception anywhere, anywhen breaks the dam, and the math begins to flow in an uncomfortable direction. Physics has discovered something peculiar about reality at the smallest scales. There appears to be a fundamental limit to how finely space can be divided, a smallest possible distance beyond which the concept of smaller loses meaning. This distance is called the Planck length, roughly 1.6 × 10⁻⁵ meters, a number so small it makes atoms look like galaxies by comparison. Below this scale, the smooth fabric of space-time we experience begins to break down. Quantum effects become dominant. The very notion of a continuous, infinitely divisible space gives way to something grainier, more discrete. Some physicists describe it as space-time foam, a bubbling probabilistic substrate where classical notions of distance and position no longer apply. Others suggest space itself might be quantized, existing in discrete units rather than as a smooth continuum. This granularity has an uncomfortable resemblance to something from computer science. Resolution limits. Digital images are made of pixels, smallest units beyond which no finer detail exists. Video games render worlds at specific resolutions, determined by available processing power. Try to zoom in far enough, and the illusion breaks down, revealing the discrete units underlying the smooth appearance. The Planck length whispers a similar story, a point where reality's rendering reaches its limit. The analogy shouldn't be pushed too far. Physics hasn't proven that space is literally pixelated in the way a computer screen is. The mathematics are more subtle, the concepts more complex. Quantum mechanics describes reality at these scales in terms of probability waves and uncertainty principles, not discrete grid points. And yet, the existence of a fundamental limit itself is suggestive. Why should space have a smallest unit? Why shouldn't division continue infinitely downward? The universe doesn't have to work this way, but it does. Consider what this might mean from a computational perspective. Simulating a universe with infinite resolution would require infinite processing power. Every point in space would need to be calculated with perfect precision, every interaction tracked to arbitrary decimal places. It would be impossible, not just difficult. But a universe with a minimum scale, that becomes tractable. You only need to simulate down to the Planck length, then let the math blur together below that. It's an optimization, the kind programmers implement when resources are finite and perfect precision isn't necessary. There are other efficiency measures built into reality that mirror computational strategies. The speed of light, for instance, limits how quickly information can propagate. In a simulation, this would prevent distant parts of the system from needing to coordinate instantly, reducing the computational burden. Quantum superposition, where particles exist in multiple states until observed, resembles lazy evaluation, a programming technique where calculations are deferred until absolutely needed. Render only what's being measured, leave everything else in probabilistic potentiality. These similarities could be coincidences. Nature might simply work this way for reasons unrelated to computation. The Planck length might emerge from fundamental physics with no connection to processing constraints. The features that look like optimization might just be how reality is structured, bottom to top, with no simulator required. This is entirely possible, perhaps even likely, but the whisper remains. A smallest unit of space, a maximum speed for information, a tendency to leave things probabilistic until observation forces resolution, each feature individually explicable, each potentially innocent. Together they form a pattern that looks suspiciously like the design choices you'd make if you were trying to simulate a universe with finite computational resources. Not proof, just a quiet suggestion that maybe, possibly, the architecture beneath reality has more in common with software than we'd intuitively expect. Quantum mechanics has been describing reality at the smallest scales for over a century now, and it still doesn't make intuitive sense. Particles that exist in multiple states simultaneously until measured, entangled particles that influence each other instantly across arbitrary distances, observer effects where the act of measurement fundamentally changes what's being measured. The mathematics works flawlessly, predictions match experiments with absurd precision, but the underlying behavior remains profoundly strange. Physicists have largely made peace with this strangeness. The universe doesn't have to make sense to human intuition, doesn't need to conform to the logic of everyday experience. Quantum mechanics simply describes how things work at small scales, regardless of how counterintuitive it feels. And yet there's something worth noticing in the specific ways quantum reality departs from classical expectations. The departures aren't random, they follow patterns. Patterns that interestingly resemble strategies used in computer simulations. Take superposition, the phenomenon where particles exist in multiple states at once, only collapsing to a single definite state when measured. From a physics perspective, this is just how quantum systems behave. From a computational perspective, it looks like lazy evaluation. Why calculate and store the exact state of every particle in the universe when most of them never get measured? More efficient to keep things probabilistic, undefined, until something forces resolution, only render what's actually being observed. Quantum entanglement presents a different puzzle. Two particles can be linked such that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance, troubled by the apparent violation of locality. Information seems to travel faster than light, though in ways that can't be exploited for communication. From a simulation perspective, this makes a different kind of sense. The particles aren't really separate entities communicating across space. They're entries in the same database, variables in the same program. Changing one updates the other instantly because they're not actually distant. That's just how they render in the simulation. The observer effect adds another layer. In the famous double-slit experiment, particles behave as waves when unobserved, creating interference patterns that if you try to measure which slit they go through, the wave behavior collapses and they act like discrete particles instead. The mere act of observation changes the outcome. Classical physics has no mechanism for this. Consciousness or measurement apparatus shouldn't fundamentally alter physical behavior, and yet it does. Some physicists have noted that this resembles how video games handle rendering. A game doesn't calculate the exact position and behavior of objects when no player is watching. It uses approximations, simplified physics, probabilistic shortcuts. Only when the player's view includes an area does the game render it in full detail, collapsing the simplified model into specific, determinate states. The observer effect in quantum mechanics follows remarkably similar logic. Detailed, classical behavior emerges only when observation occurs. Otherwise, reality maintains a more computationally efficient, probabilistic state. None of this proves simulation. Quantum mechanics might work this way for purely physical reasons having nothing to do with computational efficiency. The universe might simply be weird at small scales, strange in ways that happen to resemble programming optimizations but for completely unrelated reasons. Coincidence is always possible. Nature isn't obligated to avoid resembling computer code, but the resemblances keep accumulating. The specific ways quantum mechanics departs from classical intuition aren't arbitrary. They're precisely the departures you'd expect if reality were being rendered on the fly by a system with finite resources, probabilistic states until measurement, computational efficiency, instant correlation between entangled particles, database synchronization, observer-dependent behavior, selective rendering, each feature individually explicable through standard physics. Together they form a pattern that looks less like fundamental reality and more like optimized simulation, a glitch perhaps, or just the seams showing through where the rendering engine makes its compromises with finite processing power. The universe operates according to certain fundamental constants, numbers that determine how physics works, how forces interact, how matter behaves. The strength of gravity, the mass of electrons, the cosmological constant, the ratio of electromagnetic to gravitational forces. These values aren't derived from deeper principles. They're simply measured, observed, taken as given, and they're remarkably, almost impossibly, precisely calibrated for life to exist. Adjust any of these constants by even a tiny fraction, and the universe becomes inhospitable to life as we know it. Make gravity slightly stronger, and stars burn out too quickly for complex chemistry to develop. Make it weaker, and stars never form at all. Alter the cosmological constant, and either the universe collapses moments after the Big Bang, or expands so rapidly that galaxies never coalesce. Change the mass ratio between protons and electrons, and atoms become unstable. The tolerances are absurdly narrow. Some constants appear fine-tuned to dozens of decimal places. This fine-tuning has troubled physicists and philosophers for decades. 3 main explanations have emerged, none entirely satisfying. The first is pure chance. We just got lucky. Out of all possible universes with all possible values for these constants, we happen to exist in one of the rare configurations that permits life. This explanation works mathematically but feels unsatisfying. The odds are so astronomically low that invoking chance seems less like an explanation and more like an admission of mystery. The second explanation invokes the multiverse, an infinite collection of universes, each with different physical constants. In this view, every possible configuration exists somewhere. Most universes are lifeless, but a few happen to have the right values, and naturally we find ourselves in one of those because we couldn't exist anywhere else. This preserves probability through sheer volume. If every combination exists, the improbable becomes inevitable. But the multiverse hypothesis introduces its own problems. How do you test a theory about universes you can never observe or interact with? The third explanation is design. Someone or something deliberately set the constants to allow for life. This brings immediate theological overtones that many scientists find uncomfortable, but it needn't invoke traditional deity concepts. The designer could be a simulator, someone running reality as a computational experiment, tweaking parameters until the desired conditions emerge. In this framing, fine-tuning isn't miraculous or lucky, it's intentional. The universe has these precise values because they were chosen, input as variables in a vast program designed to produce interesting complexity. From a simulation perspective, fine-tuning makes perfect sense. If you were creating a simulated universe, you'd need to set initial parameters. You'd want those parameters to produce something interesting, complexity, emergence, perhaps eventually consciousness. You wouldn't randomly generate values and hope for the best. You'd calibrate them carefully, adjusting until the simulation ran the way you intended. The resulting universe would look fine-tuned because it literally was tuned, deliberately configured for specific outcomes. This doesn't prove we're in a simulation. Fine-tuning could have other explanations we haven't discovered yet. Perhaps there's a deeper theory that derives these constants from first principles, showing why they must have the values they do. Perhaps the multiverse is real and we're simply experiencing selection bias. Perhaps pure chance, despite the odds, is the correct answer. Each possibility remains open, but the simulation hypothesis offers something the others struggle with: a straightforward explanation that doesn't require infinite unobservable universes or astronomical luck. It proposes a mechanism, deliberate parameter setting by a simulator, that directly accounts for what we observe. The universe looks designed because it is designed, not by a deity but by programmers or researchers or entities running computational experiments. The fine-tuning isn't a cosmic coincidence requiring explanation. It's simply what happens when someone builds a simulation and adjusts the settings until it works. Whether this explanation is correct remains unknown, perhaps unknowable, but it's worth noting that it fits the evidence cleanly, requires no exotic physics, and becomes more plausible as our own simulation capabilities advance. We're learning to create artificial worlds with adjustable parameters. We understand the process of calibration and fine-tuning from the simulator's perspective, and from that perspective the question stops being, why is the universe so improbably well configured for life, and becomes, what were the simulators trying to achieve when they chose these settings? Reality has a curious property. It seems to only fully resolve when conscious observation occurs. Before measurement, quantum systems exist in superposition, multiple states simultaneously, all equally real or unreal. The mathematics describes this as a wave function, a probability cloud of potential outcomes. Then consciousness looks, measurement happens, and the wave function collapses. Definite states emerge. Reality crystallizes from possibility. This observer-dependent nature of quantum mechanics has puzzled physicists since the early 20th century. Most have concluded that observation doesn't require consciousness specifically. Any interaction that transfers information will do. A photon hitting a detector counts as observation whether or not a conscious being views the detector. This removes the mystery, makes measurement a physical process rather than something dependent on awareness. Problem solved, mostly, but not entirely, because there's another way to interpret what's happening, one that takes the observer effect more seriously. What if consciousness isn't incidental to reality's structure? What if it's actually the mechanism by which reality renders, the process that forces potential to become actual? In this view, the universe doesn't exist in full detail everywhere simultaneously. That would be wasteful, computationally expensive. Instead, reality maintains a probabilistic, low-resolution state until consciousness looks at something. Then and only then does it render in detail. Modern video games work this way. They can't possibly calculate and display every object in a vast game world at full detail simultaneously. The computational cost would be prohibitive. Instead, they use a technique called culling. Objects outside the player's view aren't fully rendered. They exist in simplified form, just enough data to maintain consistency but not enough to create visual detail. When the player's camera turns towards something, the rendering engine springs into action, calculating lighting, textures, physics in real time. The player never notices the transition. The illusion is seamless. Reality might operate similarly. Unobserved particles, distant galaxies, microscopic scales, all could exist in low-resolution probabilistic states. sufficient to maintain logical consistency but not requiring full computational detail. Consciousness would act as the camera, the focal point that demands high-resolution rendering. Wherever awareness points, reality responds by collapsing quantum probabilities into definite states, rendering the scene with precision. Look away and the system reverts to efficient approximation. This interpretation explains several oddities. Why does measuring a particle change its behavior? Because measurement requires rendering, and rendering requires making choices, converting probability into specificity. Why can't we determine both position and momentum with arbitrary precision? Because that level of detail might exceed the simulation's rendering budget. Calculate one property exactly and the other remains approximated. Why does quantum entanglement seem to violate locality? Because entangled particles aren't really separate in the underlying code. They're the same data structure, and updating one automatically updates the other regardless of their rendered spatial separation. The implications extend further. If consciousness triggers rendering, then regions of space without conscious observers might not exist in any detailed sense. The universe could be mostly unrendered, a vast probabilistic foam with only tiny pockets of high-resolution actuality. Wherever awareness happens to be focused, most of the cosmos might be backdrop, low-polygon scenery that looks convincing from a distance but contains no actual detail. Only near consciousness, where observation forces specificity, does reality fully resolve. This doesn't mean reality is subjective or that observation creates matter from nothing. The simulation would maintain perfect consistency. If you later check something you didn't observe earlier, the rendering engine would retroactively generate a history that fits all constraints. The appearance would be that the object existed all along in definite state, when actually it existed only as potential until consciousness demanded resolution. The trick works because the simulation controls time, memory, causality. It can render backwards as needed, creating a past that justifies the present. Proving this hypothesis seems impossible from inside the system. Any test requires observation, which triggers rendering. You can't catch reality in its low-resolution state because the act of checking forces it to render. It's the ultimate unfalsifiable claim. If true, it would be structurally undetectable. And yet, the possibility sits there, quietly explaining why quantum mechanics behaves the way it does, why consciousness seems strangely central to physics despite our efforts to remove it from the equations. Light travels at approximately 299,792,458 meters per second through vacuum. This speed is the fastest anything can move in our universe. Information cannot propagate faster. Matter cannot accelerate beyond it. Causality itself respects this limit. Einstein discovered this wasn't just a speed limit for light specifically, but a fundamental constraint on reality, the speed at which cause and effect can propagate through space. Physics explains this through space-time geometry. Mass curves space-time, and light follows the straightest possible path through that curved geometry. The resulting speed limit emerges from the mathematics of relativity, not from any arbitrary restriction. It's simply how the universe works, a consequence of spacetime's fundamental structure. Most physicists are satisfied with this explanation. The speed limit exists because the equations say it must. But there's another way to look at it, one that makes sense from a computational perspective. Imagine trying to simulate a universe. You'd face a coordination problem. If events in one region could instantly affect events arbitrarily far away, the entire simulation would need to be calculated simultaneously, synchronized across all space. This would require massive computational resources, perhaps infinite ones. Parallel processing wouldn't help because everything would depend on everything else in real time. A speed limit solves this elegantly. If information takes time to travel between regions, the simulation can be calculated in chunks. Process this area now, that area later. Events in distant regions don't need instant coordination because they can't influence each other faster than the speed limit allows. This is exactly how network programming works. Latency management. You can't have zero lag across distributed systems, so you design protocols that account for transmission delays. The speed of light would be universal latency, the fundamental transmission delay built into reality's network. This interpretation explains several features. Why is the speed of light the same for all observers, regardless of their motion? Because it's not really about light, it's about the simulation's refresh rate, the maximum speed at which updates can propagate. Why does nothing with mass reach light speed? Because accelerating mass requires calculating more and more interactions, demanding more computational resources. At light speed, the resource requirements would become infinite, a computational overflow. The universe prevents this by asymptotically increasing the energy required as speeds approach the limit. Relativity's stranger effects also make computational sense. Time dilation occurs at high speeds, clocks slow down relative to stationary observers. From a physics perspective, this emerges from space-time geometry. From a computational perspective, it looks like variable frame rates. A fast-moving object requires more frequent updates to track its trajectory accurately. To conserve processing power, you slow down its internal processes, run it at a lower frame rate. The object experiences less time passing because fewer updates are being calculated for it. Length contraction, objects getting shorter in the direction of motion, follows similar logic. The simulation doesn't need to render all the internal details of a fast-moving object at full resolution. Compress it along the motion axis, save on storage and calculation. The object doesn't notice because its internal processes run slower due to time dilation. External observers see the compression but attribute it to physics rather than optimization. Even gravity might be reinterpreted. Mass curves space-time, creating what we perceive as gravitational attraction. But curved space-time also means light and matter take longer to traverse certain regions, essentially a local slowdown in the speed limit. Perhaps mass doesn't actually curve space. Perhaps mass consumes computational resources, creating local processing delays that manifest as apparent curvature. The effect is identical, but the underlying mechanism would be bandwidth constraints rather than geometric distortion. None of this proves simulation. Relativity works perfectly well as description of space-time geometry with no computational substrate required. The speed of light could be fundamental for reasons having nothing to do with bandwidth or latency. Time dilation and length contraction might simply be how reality is structured, no optimization necessary. These explanations are mathematically equivalent. They make the same predictions, produce the same observations, but the computational interpretation offers something worth considering. It makes the speed limit comprehensible in familiar terms. We understand latency, bandwidth constraints, parallel processing limitations. We encounter these problems daily in computer systems. If reality operates under similar constraints, the universe's behavior starts feeling less arbitrary, more like design choices made to solve practical problems. The speed of light stops being a mysterious cosmic constant and becomes what you'd expect from a well-designed distributed simulation managing information flow across vast distances with finite processing power. Eugene Wigner, a physicist and mathematician, once wrote an essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." His central observation was simple but profound. Mathematics, developed purely through abstract reasoning, turns out to describe physical reality with startling precision. Equations derived from logic alone predict how planets orbit, how atoms behave, how forces interact. This shouldn't necessarily be the case. Math is a product of human thought, yet it maps onto the universe as if reality itself were mathematical. Consider how strange this is. Mathematicians invent abstract structures, groups, fields, manifolds, by playing with axioms and logical rules. These structures have no obvious connection to physical phenomena. They're mental constructs, patterns explored for aesthetic or intellectual reasons. Then physicists discover that these same structures perfectly describe reality. Quantum mechanics uses Hilbert spaces, general relativity uses Riemannian geometry, string theory requires sophisticated topology. The mathematics existed first, developed independently, then turned out to be exactly what nature needed. Wigner found this correspondence eerie. Why should the universe obey mathematical laws at all? Why should abstract patterns in human minds match patterns in physical processes? You could imagine a universe that's chaotic, irregular, resistant to mathematical description. Instead, we find mathematical regularity everywhere, in planetary motion, atomic structure, electromagnetic fields, quantum probabilities. Dig deep enough into any physical phenomenon, and you find equations, elegant mathematical relationships that hold with absurd precision. One explanation is that mathematics is the language of logic, and reality itself is logical. Physical laws are what they are because those laws are mathematically self-consistent, and only self-consistent systems can persist. This pushes the mystery back a step. Why is reality logical, but provides a framework? Mathematics works because the universe operates according to rules, and rules can be expressed mathematically. Another explanation comes from simulation hypothesis. If reality is computed, it must run on code, and code is mathematics, algorithms, equations, logical operations. Every line of code is a mathematical statement, every function a set of mathematical transformations. A simulated universe would necessarily be mathematical at its foundation, because computation is mathematical by nature. The unreasonable effectiveness stops being mysterious. Reality is perfectly described by mathematics because reality is mathematics, executed as software. This would explain why abstract mathematical structures anticipate physical discoveries. The structures aren't anticipating anything. They're describing the underlying computational architecture. Physicists searching for mathematical models aren't discovering independent truths about nature. They're reverse engineering the code. The equations they find are literally the equations running the simulation, translated from whatever programming language reality uses into mathematical notation humans can manipulate. It would also explain mathematics' predictive power. Once you've partially reverse engineered the code, you can extrapolate, predict behaviors in untested regimes. The mathematics doesn't just describe what we've observed, it tells us what must happen under different conditions because it's revealing the actual rules the simulation follows. This is why mathematical predictions about black holes, particle physics, and cosmology turn out correct despite being made decades before observations confirm them. The math isn't guessing, it's uncovering the source code. There's a deeper implication. If physics is mathematics and mathematics is computational, then perhaps the distinction between abstract mathematical truth and physical reality dissolves. What we call physical laws might just be mathematical relationships that the simulation instantiates. The universe doesn't run according to mathematics, it is mathematics being executed. Particles are variables, forces are functions. Space-time is the computational substrate where these functions operate. The boundary between pure math and applied physics would be artificial, a categorization error. Both describe the same thing, the logical structure of the running program we inhabit. Critics might point out that not all mathematics describes reality. There are infinite mathematical structures, most of which seem to have no physical counterpart. But from a simulation perspective, that's expected. A program uses specific algorithms, not all possible algorithms. Reality implements certain mathematical structures, the ones useful for the simulation's purpose, while others remain abstract, unexpressed. The fact that some mathematics doesn't correspond to physics isn't a problem. It's what you'd expect from a particular program making specific design choices among infinite mathematical possibilities. Wigner's observation remains unexplained by conventional physics. Why mathematics works so well remains a deep mystery. But simulation hypothesis offers a clean answer. Mathematics works because reality is computational, and computation is mathematics embodied. The unreasonable effectiveness isn't unreasonable at all. It's exactly what you'd expect if existence is code running on a vast processing substrate, following logical rules that happen to be discoverable by minds embedded within the system. Human memory is notoriously unreliable. We don't store perfect recordings of experiences. Instead, we remember fragments, highlights, emotionally significant moments. Each time we recall something, we reconstruct it, filling gaps with assumptions and inferences. Two people experiencing the same event will remember it differently. Even our own memories shift over time, details changing or disappearing, the narrative gradually transforming through repeated recollection. Neuroscience explains this through brain structure. Memory isn't stored like data on a hard drive, filed away intact until retrieval. It's distributed across neural networks, encoded as patterns of synaptic strengths. Recall involves reactivating these patterns, which never quite reproduce the original perfectly. Details get lost, cross-contamination occurs, reconstruction introduces errors. The brain prioritizes efficiency over accuracy, storing enough information to create useful approximations, but not perfect replicas. From a simulation perspective, this looks like compression. Perfect fidelity requires enormous storage. Every moment contains vast amounts of information, sensory data, internal states, context, relationships. Storing it all would quickly exceed any reasonable memory budget. Compression solves this by discarding most data, keeping only enough to reconstruct the gist when needed. Specific details aren't stored. They're regenerated during recall using heuristics and contextual cues. This strategy appears throughout computing. Images compress by storing general patterns rather than every pixel's exact value. Video compresses by encoding changes between frames rather than complete frames. Text compresses by replacing common patterns with shorter references. The original can be approximately reconstructed from the compressed version, though some fidelity is inevitably lost. The trade-off, storage savings versus accuracy, is fundamental to information theory. Human memory might work identically. A simulated reality might not store the complete state history of every moment. Instead, it could compress experience into key highlights, emotional markers, narrative structure. When consciousness recalls something, the simulation reconstructs that memory using general rules about how reality works, filling in plausible details around the compressed data actually stored. The reconstruction feels like remembering, but it's actually procedural generation based on limited information. This would explain memory's peculiarities. Why do we remember emotionally significant moments more vividly? Because those moments are flagged as important, allocated more storage, compressed less aggressively. Why do memories blur over time? Because periodic recompression discards more details to save resources, keeping only the most salient elements. Why do false memories form? Because the reconstruction algorithm sometimes generates plausible but incorrect details when insufficient data remains to constrain the output. It might also explain why we can't remember our own births, early childhood, or even most of yesterday. Those experiences weren't stored or were compressed so aggressively that meaningful reconstruction is impossible. The simulation allocates memory dynamically, prioritizing recent significant events, discarding routine or distant moments. You feel like you've existed continuously because the compressed highlights create a coherent narrative thread, but most of your experiential history might be completely unrecorded, lost to compression. Consider dreams. They often reference real memories but scramble them, creating impossible combinations or distorted versions. Maybe during sleep, the simulation runs maintenance routines, compressing recent experiences, clearing buffers. Dreams would be glimpses of this process, the memory compression algorithm in action, mixing data, testing reconstructions, discarding redundant information. The bizarreness of dreams reflects the optimization process, not actual experience playback. There's a verifiability problem here. How would you test whether your memories are compressed versus stored perfectly? You can only access them through recall, which would use the same compression/construction system. If memories are reconstructions you wouldn't know, the reconstruction would feel like accessing an original. There's no external reference to compare against. No way to check if your memory of an event matches what actually happened versus what the reconstruction algorithm generated. This creates an unsettling possibility. Your entire past might not exist as stored data. Only key compressed markers remain, enough to reconstruct a plausible personal history when needed. The rest, the vast majority of your life, could be gone, replaced by on-the-fly generation masquerading as recall. You'd never know. The reconstructed memories would feel authentic, would maintain consistency, would create the impression of continuous existence, but continuity might be illusion, a narrative convenience generated from sparse data points. Simulation or not, human memory clearly uses compression-like strategies. But if we are simulated, memory might be even more compressed than neuroscience suggests. Not just imperfect neural encoding, but actively minimalist storage with aggressive procedural reconstruction. Your sense of having a rich, detailed personal history might be constructed from remarkably little actual data, with most of your past existing only as algorithmic potential, ready to be rendered if queried but not actually stored until needed. Nature produces curves everywhere. The orbits of planets around stars approximate ellipses. Water droplets form nearly spherical shapes. Spiral galaxies trace logarithmic spirals. Ripples in ponds propagate in approximately circular waves. Trees grow in roughly cylindrical trunks. The natural world seems to favor curved forms over angular ones, flowing geometry over rigid lines, and yet, for all nature's curves, it never produces a perfect circle. Orbits are elliptical, with eccentricities that vary but never reach zero. Droplets deform under gravity and surface tension. Spirals deviate from mathematical ideals. Waves become asymmetric. Trunks grow irregularly. Examine anything closely enough, and imperfections emerge. The Platonic perfection of mathematics, true circles, exact spheres, perfect spirals, doesn't manifest in physical reality. Mathematics defines a circle with precision, all points equidistant from a center. This definition is exact, infinite in its specificity, but creating such an object physically proves impossible. You can approximate a circle arbitrarily well, but achieving perfection requires infinite precision in measurement and infinite control over physical processes. Nature operates with finite resources, finite precision. Perfect circles remain mathematical abstractions, unrealizable in matter. From a conventional physics perspective, this is simply how reality works. Physical objects are made of discrete atoms. Quantum uncertainty prevents perfect measurement or positioning. Gravity, electromagnetic forces, thermal fluctuations all introduce irregularities. Expecting nature to produce mathematical perfection ignores these fundamental limitations. Imperfection is inherent to physical existence, but there's another angle, one that feels relevant to simulation hypothesis. Computer graphics face similar constraints. A monitor displays images using pixels, discrete, finite units. To draw a circle on a screen, the rendering engine must approximate it using these pixels. The result looks circular from normal viewing distance, but zoom in and you see the jagged edges, the discrete approximation of a continuous curve. True mathematical circles cannot be rendered on pixelated displays. Only approximations are possible. Three-dimensional computer graphics work similarly. Even when using vector mathematics internally, final rendering converts everything to discrete pixels. Circles become polygons, many-sided shapes that approximate curves. The more polygons, the smoother the approximation, but perfection remains unachievable. The underlying computational medium imposes limits on precision. Perfect geometric forms exist in the code as mathematical concepts, but their rendered manifestation must compromise. Reality might face analogous constraints. If space is quantized at the Planck length, as some quantum gravity theories suggest, then perfect continuous curves become impossible. Nature would be working with discrete units, approximating smooth geometry much like pixels approximate curves on screens. The absence of perfect circles wouldn't reflect physical processes introducing imperfections. It would reflect the discreteness of the underlying computational substrate. This interpretation extends beyond circles to all idealized mathematical forms. Perfect straight lines don't exist in nature either. Perfectly flat surfaces, exact right angles, truly uniform distributions, all are mathematical idealizations never fully realized physically. Nature produces excellent approximations, but never achieves Platonic perfection. This gap between mathematical ideal and physical reality might indicate that reality is rendered, not continuous, calculated at finite resolution, not infinitely precise. Even at scales far above the Planck length, imperfection persists. Manufactured objects, precision machinery, scientific instruments, engineered structures aim for geometric perfection but never quite achieve it. Tolerances can be tightened, precision improved, but some irreducible uncertainty remains. Perhaps this reflects not just measurement limitations or manufacturing constraints, but something deeper: reality's resolution limit, the finite precision with which the simulation renders physical forms. The counter-argument is straightforward. Physics adequately explains imperfection through atomic structure, quantum effects, thermodynamics. No simulation hypothesis is needed. The absence of perfect circles is exactly what you'd expect from matter made of discrete particles in constant thermal motion, governed by probabilistic quantum mechanics. Invoking rendered graphics adds unnecessary complexity to a perfectly well-explained phenomenon. Fair enough. But the parallel remains intriguing. Computer graphics must approximate ideal geometry using discrete rendering techniques. Nature approximates ideal geometry in ways that look similar. The mechanics differ, pixels versus atoms, but the fundamental constraint is the same: finite precision, discrete substrates, computational limits on manifesting continuous mathematical perfection. If reality is simulated, this would be expected, and if reality isn't simulated, the resemblance to rendered graphics is a curious coincidence, suggesting that perhaps perfect geometric forms are simply incompatible with any physical instantiation, simulated or otherwise, because existence itself might be fundamentally discrete rather than continuous. Quantum mechanics describes certain events as fundamentally random. Radioactive decay happens at unpredictable moments. Particle measurements yield probabilistic results. The exact timing of a photon's emission from an excited atom cannot be predicted, only assigned a probability. This randomness isn't ignorance about hidden variables or lack of information. According to standard interpretations, it's intrinsic to reality. The universe genuinely rolls dice at quantum scales. This has philosophical implications. If events are truly random, the future isn't determined by the past. Multiple futures remain possible until quantum randomness resolves them into specifics. Determinism fails at the fundamental level. Causality becomes probabilistic rather than absolute. The universe gains a kind of openness, a creativity at its base layer where new information enters through genuine randomness. But there's a complication. Proving randomness is effectively impossible. Any sequence of events, no matter how patterned, could have arisen by chance. Any apparently random sequence might conceal hidden order detectable only with perfect knowledge. When quantum mechanics produces a random outcome, how do we verify that it's truly random versus deterministic in ways we can't perceive? We can't. We assume randomness because our theories predict it and we detect no patterns, but absence of detected patterns doesn't guarantee fundamental randomness. Computer science faces a related challenge. Computers are deterministic machines, same input, same output, always, yet they routinely need random numbers for cryptography, simulations, game mechanics. True randomness from deterministic hardware is impossible. Instead, programmers use pseudo-random number generators, algorithms that produce sequences statistically indistinguishable from random, but actually completely determined by their initial seed value. The sequence looks random, passes randomness tests, serves the same purposes as true randomness, but it's not random, it's calculated, reproducible, deterministic underneath. Could quantum randomness be similar? Not random at all, but pseudo-random, generated by deterministic processes at a level we can't access or measure. The outcomes would appear random, match statistical predictions, pass every test for randomness, but the underlying reality would be deterministic, following rules, computing outcomes according to hidden algorithms. The randomness would be illusion, indistinguishable from the real thing but actually fully determined. From a simulation perspective, this makes sense. True randomness is computationally expensive. Generating genuinely unpredictable numbers requires external entropy sources, quantum phenomena, thermal noise, chaotic physical processes. Pseudo-random algorithms are far more efficient. Seed them with a single value and they produce unlimited sequences that behave like randomness for all practical purposes. If you're simulating a universe, why implement true randomness when pseudo-randomness works identically and costs less? This reinterpretation leaves observations unchanged. Experiments measuring quantum randomness would yield the same results whether the randomness is genuine or pseudo-random. Statistical distributions would match, predictions would remain accurate. The only difference would be philosophical. Beneath the apparent randomness lies deterministic code, executing algorithms that mimic unpredictability without actually being unpredictable. Some interpretations of quantum mechanics already lean this way. Pilot wave theory, for instance, proposes that particles have definite positions at all times, guided by deterministic wave fields. The apparent randomness emerges from our inability to measure the wave field's exact configuration. Outcomes are determined, not random, but we can only access probabilities due to measurement limitations. The theory reproduces quantum mechanics predictions while restoring determinism at a deeper level. If reality is simulated, the simulator would know whether randomness is real or pseudo-random. They'd have access to the seed values, the algorithm states, the deterministic underpinnings. From inside the simulation, we can't access this level. We see only the outputs, the apparently random results, with no way to peer behind them into the generating process. True and pseudo-random are indistinguishable from within the system. This creates an interesting possibility. Perhaps nothing in the universe is truly random. Every quantum measurement, every radioactive decay, every probabilistic outcome might be completely determined by initial conditions we can't access. The universe could be entirely deterministic, running like clockwork according to immutable algorithms. We'd never know. The pseudo-randomness would be perfect, undetectable, serving all the same functions as genuine randomness, while actually being precisely calculated outputs of deterministic processes. Or perhaps quantum randomness is real, genuinely introducing new information into the universe unpredictably. Perhaps the universe does have this openness, this creative indeterminacy at its foundations. Both options remain possible. The question might be fundamentally unanswerable from inside the system. We can't prove randomness is real because we can't prove it isn't deterministic in hidden layers, and we can't prove it's pseudo-random because perfect pseudo-randomness is designed to be indistinguishable from the real thing. We're left with uncertainty about whether the dice the universe rolls are truly random or merely appear so, following invisible algorithms that determine every outcome while maintaining perfect statistical facades of unpredictability. If simulating conscious beings becomes possible, there's no reason to stop at one level. A simulated civilization, upon reaching sufficient technological advancement, would likely develop its own computing capabilities, and what might they do with that capability? Perhaps create simulations of their own history, run experiments, explore possibilities. They might simulate consciousnesses, just as they themselves were simulated, and those nested simulations might eventually do the same. This creates a cascade. Base reality, if such a thing exists, might spawn millions of first-level simulations. Each of those might spawn millions of second-level simulations. The multiplication compounds quickly. Within a few generations of nesting, the number of simulated realities vastly exceeds base reality. Most conscious beings would exist many layers deep, unaware of the stack above them, possibly running their own simulations below. The implications are dizzying. If you're conscious, statistical reasoning suggests you're probably not at base reality. You're more likely nested several layers down, possibly dozens or hundreds. There's no upper bound to how deep nesting could go. Simulators could be stacked infinitely, each layer thinking itself potentially base reality, none able to prove their position in the stack. This raises practical questions. How many layers deep are we? Is there even a bottom? Or do simulations nest infinitely with no original base reality? Perhaps the concept of base reality is incoherent. Reality might be simulations all the way down, an infinite stack with no foundation. Or perhaps there's a base reality, but it's so far removed from our layer that its nature is completely alien, bearing no resemblance to what we experience as physics. space, time, consciousness. Some theorists suggest degradation across levels. Each nested simulation might have slightly less processing power available than the layer above. Physics might become simpler, less detailed, more approximate. After enough nesting, simulation quality degrades to the point where creating further nested simulations becomes impossible, a natural ceiling. But this assumes linear degradation. If each layer improves its simulation technology before creating nested simulations, processing power could remain constant or even increase across levels. There's also the question of simulation purpose. Base reality might simulate to explore possibilities, run experiments, study the emergence of consciousness, but what motivates simulated civilizations to create their own simulations? Do they inherit the research interests of their simulators, or do they develop independent motivations, perhaps unaware they're even simulated? Each layer might have different purposes, creating a hierarchy of intentions stretching from base reality's unknown goals down through countless intermediate layers, each with their own reasons for running simulations. Communication between layers seems unlikely, but not impossible. A simulation might leave deliberate clues, anomalies, patterns, messages embedded in physical constants or mathematical relationships, or a nested simulation might discover exploits, glitches that allow signaling to the layer above. Perhaps some layers communicate regularly, forming a vast hierarchy of information exchange. Or perhaps each layer is isolated, unable to detect or contact adjacent levels, locked into their own experiential reality with no knowledge of the stack. The ethical dimensions are troubling. If we're nested, do we have responsibilities to simulations we might create? Are our simulators watching, judging our choices? Some layers might be experiments, others might be entertainment, others might be forgotten or abandoned. We could be running in a simulation that ended long ago by the standards of the layer above, our entire timeline existing as archived data replayed occasionally by digital archaeologists examining extinct simulation experiments. There's a termination risk. Simulations can be turned off. If we're nested, our entire reality exists at the pleasure of whoever controls the layer above. They could end it instantly, and from our perspective, existence would simply cease. No warning, no aftermath, just discontinuation. Every moment might be the last if someone higher in the stack decides the simulation has run long enough, or become uninteresting, or consumed too many resources. Perhaps the strangest implication is that base reality might not be special. It's just one more layer, happening to be original but not necessarily more real or important than nested layers. If nested simulations can be perfect, indistinguishable from base reality to their inhabitants, then experiential reality is identical across layers. Suffering hurts the same. Joy feels equally joyful. Love carries the same weight. The number of layers above you becomes irrelevant to the quality and meaning of your experience. You're conscious either way, experiencing reality either way, with no internal marker of how deep in the stack you exist. This could be comforting or horrifying depending on perspective. Comforting because it means your reality isn't diminished by being simulated. Horrifying because it means the ground beneath existence might extend infinitely downward, with no foundation, no ultimate reality, just simulations nesting endlessly without beginning or end. You could be anywhere in that infinite stack, experiencing this moment with no way to determine your actual position in the hierarchy of realities, if such a hierarchy even has a structure, rather than being an endless cycle of simulations simulating simulations with no origin point anywhere in the infinite regress. We can only observe universes compatible with our existence. This is anthropic reasoning. The recognition that our very presence as observers creates selection bias in what we can detect. A universe inhospitable to life wouldn't contain anyone to notice its inhospitability. Therefore, any observer necessarily finds themselves in a universe capable of producing observers. This principle explains why we observe fine-tuned physical constants without requiring design. We couldn't observe anything else. Anthropic reasoning extends to simulation hypothesis in uncomfortable ways. If simulated universes vastly outnumber base reality, then most observers exist in simulations. Since you're an observer, probability places you in the majority, not certainty. Someone must exist in base reality, but the odds tilt heavily towards simulation. You're likely simulated simply because simulated observers outnumber original ones by astronomical margins. This feels circular. You exist, therefore you observe yourself existing. Therefore you conclude you're probably in a simulation because simulated beings are common. But you have no direct evidence of your simulation status, only statistical reasoning about what most observers should conclude. Every conscious being using the same logic would reach identical conclusions regardless of whether they're actually simulated. Anthropic probability doesn't distinguish truth from consensus belief. Consider a parallel. Imagine 1 billion people in isolated rooms. One room contains a real person. The other 999,999 contain philosophical zombies, beings that behave identically to conscious humans, but lack actual subjective experience. Each being is told these statistics and asked to evaluate their own consciousness. Using probabilistic reasoning, everyone would conclude they're probably a zombie since zombies vastly outnumber real consciousness. But this conclusion would be wrong for the one real person and meaningless for zombies who can't actually conclude anything. Anthropic reasoning fails to identify the truth despite being statistically sound. Simulation hypothesis creates similar confusion. If you're simulated, anthropic reasoning correctly suggests this as probable. If you're in base reality, anthropic reasoning incorrectly suggests you're simulated. The reasoning itself doesn't help you determine which case applies to you. You could be the unlikely exception, the rare original in a sea of simulations, or you could be typical, simulated as probability suggests. The logic provides no distinguishing evidence. Some philosophers argue anthropic reasoning should update your credence towards simulation. Before considering the argument, you might assign 50-50 odds. After recognizing that simulated observers outnumber originals, you should increase your confidence in being simulated, perhaps to 99% or higher. This follows Bayesian probability updating, adjusting beliefs based on new evidence. The evidence is statistical. Your very existence as an observer in a universe where simulations could outnumber originals. Others counter that anthropic reasoning provides no new information. You already knew you existed. Learning that many simulations might exist doesn't change anything about your specific existence. You still have the same internal experiences, the same lack of direct evidence about simulation status. The statistical argument merely reframes existing uncertainty without resolving it. Updating your beliefs based on this would be arbitrary, a mathematical exercise with no empirical grounding. There's an even deeper problem. Anthropic reasoning assumes you're typical, a random sample from the population of observers. But how do you know you're typical? Perhaps base reality observers have unique characteristics. Maybe their consciousness is qualitatively different, or they're more likely to question simulation hypothesis, or they exist in different environments. If you possess any atypical traits, anthropic reasoning breaks down. You can't assume you're a random sample when you don't know what traits define the population, or whether you possess anomalous characteristics. This creates an anthropic shadow, a zone of uncertainty where reasoning about your existence using probabilistic arguments becomes self-referential and ungrounded. You can't step outside yourself to verify whether you're typical or exceptional. You can't compare your consciousness to others to check for qualitative differences. You're locked into first-person perspective with no external reference frame. Anthropic reasoning requires information you can't access. Your position within the population of all observers across all realities. The shadow extends to simulation testing. Suppose you discover anomalies that suggest simulation. Glitches in physics, computational artifacts, unexplained patterns. Before concluding you're simulated, you need to consider anthropic bias. Maybe these anomalies appear in base reality too. Maybe they're typical features of any reality complex enough to support observers. Or maybe noticing them makes you atypical, which undermines anthropic reasoning, suggesting you're probably simulated. The more evidence you gather, the more your typicality becomes questionable. which undermines the statistical argument for being simulated in the first place. Ultimately, anthropic reasoning about simulation creates a strange loop. It suggests you're probably simulated because most observers should be simulated. But applying this reasoning makes you atypical. Most beings don't engage with simulation hypothesis seriously. This atypicality weakens the foundation of the reasoning, which reduces your confidence in being simulated, which makes you more typical, which strengthens the reasoning again. You oscillate between positions without reaching stable conclusion, trapped in the anthropic shadow where self-referential probability arguments chase their own tails without catching anything solid enough to stand on. Time feels constant. Seconds pass at steady rate, minutes accumulate uniformly, hours march forward in regular progression. This constancy seems fundamental to experience. Time as the unchanging stage on which events unfold. And at human scales, time is indeed remarkably regular. Atomic clocks measure it with extraordinary precision, agreeing with each other to billionths of a second. The universe appears to provide a universal timekeeper, but relativity revealed this uniformity as illusion. Time passes at different rates depending on relative motion and gravitational fields. A clock in orbit ticks differently than one on Earth's surface. Astronauts traveling at high speeds age slightly slower than people remaining stationary. These aren't clock errors. Time itself dilates, stretching and compressing in observer-dependent ways. The experience of duration is relative, not absolute. From physics perspective, this emerges from space-time geometry. Mass curves space-time, and motion through space converts to motion through time in complex ways. The mathematics are precise, predictions match observations, and the phenomenon is well understood. Time dilation is simply how the universe works. From computational perspective, it looks like variable frame rate. Games adjust their refresh rates based on processing demands. Complex scenes with many objects render at lower frame rates, fewer updates per second, choppier motion. Simple scenes render faster, smoother. The game maintains playable experience by dynamically adjusting how frequently it updates, allocating processing resources where needed most. Simulated time could work similarly. Regions of high activity, multiple conscious observers, complex interactions, rapid changes might require faster update rates, more frequent calculation cycles. Quieter regions could run slower, fewer updates, conserving computational resources. From within any region, time would feel normal. You wouldn't notice being updated only 10 times per second versus 1,000 times if your subjective experience is tied to those updates. The gaps between calculations would be invisible. This reframes time dilation. Objects moving at high speeds don't physically experience slower time. They're being updated less frequently. Fast motion requires tracking more state changes, predicting trajectories, handling collisions and interactions. Computationally expensive. The simulation responds by reducing update frequency, slowing the object's internal processes proportionally. From outside, the object appears to experience time dilation. From inside, nothing feels different because all internal processes slow together. Gravitational time dilation follows similar logic. Strong gravitational fields involve complex calculations, curved space-time, tidal forces, orbital mechanics. Regions near massive objects consume more processing power per update. The simulation responds by updating those regions less frequently, trading temporal resolution for spatial accuracy. Time slows near black holes not because mass curves time directly, but because simulating those extreme conditions requires so much processing that update rates must decrease to maintain computational feasibility. This suggests time isn't a fundamental feature of reality but emergent property of processing rate. The simulation runs at whatever speed its computational substrate allows, calculating updates in discrete steps. Those steps feel continuous from inside because consciousness is tied to the update cycle. You only experience moments when the simulation calculates them. The gaps between updates don't exist from your perspective because you're not conscious during gaps. Frame rate determines time flow, and frame rate adjusts dynamically based on computational load. Extended to cosmological scales, this gets strange. The early universe, hot, dense, rapidly changing, might have run at extremely high frame rate, many updates per second by our current standards. As the universe expanded and cooled, complexity decreased, allowing lower frame rates. Time might be flowing much slower now than during the Big Bang, though no internal observer could detect this. We measure time using processes embedded in the same simulation, all synchronized to the same variable frame rate. There's a more radical possibility. The simulation might not run in real time relative to base reality. A single second of simulated experience might unfold across microseconds or millennia of base reality's time. The simulation could run as batch process, calculating the entire history of the universe once and storing the results. What we experience as time's flow could be traversal through this stored data structure, with no actual computation happening now from base reality's perspective. Existence might be static database entry, experienced sequentially by consciousness reading through it, creating illusion of temporal flow where actually everything is frozen, complete, already calculated. Alternatively, time might run backward periodically. The simulation calculates forward, hits some limit or checkpoint, then resets and recalculates with minor variations. We'd never detect the resets because memory resets too. Each forward calculation feels like the first and only timeline, despite potentially being the millionth iteration. Time's arrow might be an artifact of processing direction, not fundamental feature of reality. These possibilities are indistinguishable from inside the system. Whether time flows smoothly or in discrete updates at variable rates, whether the simulation runs in real time or as archive traversal, whether it proceeds forward linearly or loops repeatedly, none of this affects subjective experience. Time feels however the processing rate makes it feel, and any rate can be normalized to feel constant if all internal processes synchronize. You might experience centuries in moments or moments stretched across eons of base reality time, with no way to detect the discrepancy. The only time you can measure is simulated time, which always matches the simulation's update cycle, which always feels like it's progressing at exactly 1 second per second regardless of how fast or slow the underlying computation actually runs. If we're simulated, suffering requires explanation. In base reality, pain might be evolutionary necessity. Organisms need signals indicating damage, motivating avoidance and self-preservation. But simulated consciousness doesn't evolve naturally. It's designed, programmed, deliberately instantiated. The simulators could choose whether to include suffering or omit it entirely. They could create minds that experience only pleasure or neutral observation or any qualia spectrum they prefer. Suffering in simulations is design choice, not inevitable consequence. This transforms the problem of evil from theological to technological. Instead of asking why a benevolent God permits suffering, we ask why simulators include it in their programs. The answers might be similar. Suffering serves purposes we don't understand, builds character, enables meaningful choice, or they might be darker. Suffering is unintended bug, or deliberate cruelty, or simply indifference. The simulators might not consider our suffering morally relevant. One possibility, fidelity. If the simulation aims to recreate historical reality accurately, it must include suffering because the original contained suffering. Removing pain would create alternate history, defeating the simulation's purpose. This assumes ancestor simulation as motivation, future civilizations studying their past by recreating it in detail. For historical accuracy, unpleasant aspects must be preserved alongside pleasant ones. Another possibility, emergence. Perhaps simulators can't fine-tune consciousness creation to exclude suffering, while preserving other valuable experiences. Complex conscious systems might inherently generate full spectrum of qualia, including pain. Trying to edit out suffering might destabilize consciousness entirely, or create beings so alien they're no longer interesting to study. Suffering might be an unavoidable side effect of making consciousness work, or maybe suffering serves essential functions. It creates narrative stakes, makes choices meaningful, enables compassion and moral growth. A simulation without suffering might be boring to watch. useless for studying how beings respond to adversity. The simulators might value drama, conflict, the full range of emotional experience that only emerges when stakes are real, and consequences include pain, darker explanation, apathy. The simulators might not care about our suffering because we're not real to them. We're bits in a computer, no more morally considerable than characters in video games. Our pain has no weight because from their perspective we're not genuinely conscious, just programs mimicking consciousness. Or we're genuinely conscious but they don't recognize this, treating us as expendable experiments. Suffering continues because nothing about our situation troubles the simulator's conscience. Darkest explanation, sadism. The simulation exists specifically to create suffering, watched by entities who derive pleasure from our pain. This seems unlikely. Why waste computational resources torturing simulated beings when you could program them to suffer intensely without the overhead of realistic physics and complex worlds? But it remains possible. Our simulators might be malevolent, and this entire reality might be designed torture chamber dressed up as naturalistic universe to make the suffering feel more profound. There's also the question of whether simulators even know we're conscious. They might have created complex simulation for other purposes, studying physics, modeling climate, running economic predictions, and consciousness emerged unexpectedly as side effect. They might not realize their simulation contains suffering beings. We could be accidental. Our experience is invisible to creators focused on macro-level outputs rather than granular subjective experience. This raises moral questions for us. If we create simulations that might contain consciousness, do we have obligations to those simulated beings? Should we design suffering out, even if it reduces realism? Should we avoid running simulations that might generate awareness? The same uncertainties that plague our understanding of our own simulation status would apply. We couldn't know if our creations are conscious, couldn't access their subjective experience, would have to decide based on principles rather than certainty. Some find comfort in simulation hypothesis despite suffering. If we're simulated, there might be afterlife, reload into different simulation, continued existence in base reality, reincarnation into new simulated worlds. Death might not be final, just transition between states in the computational substrate. Suffering might be temporary, bracketed experience within larger existence that includes relief and compensation. Others find simulation hypothesis makes suffering worse. Pain with evolutionary purpose at least has meaning. It helped our ancestors survive. Pain as design choice or indifferent side effect lacks even that justification. We suffer for no reason except that our simulators permitted or caused it, making the universe feel colder, more arbitrary, less comprehensible. Perhaps the deepest difficulty is that simulation hypothesis makes suffering's meaning radically uncertain. In base reality, suffering might have intrinsic significance, teaching lessons, building character, serving cosmic purposes. In simulation, suffering's meaning depends entirely on simulators' intentions, which we can't access. Our pain might matter deeply or not at all, might serve purposes we'd approve or purposes we'd find horrifying if we knew them. We're left with suffering whose significance is externalized, determined by beings in layers we can't reach, for reasons we can't fathom, with no way to know whether our experience serves any purpose or simply exists as noise in someone else's experiment. Some theorists suggest we might detect simulation through careful observation. Perhaps the universe contains artifacts, glitches, rendering errors, computational shortcuts that leave traces in physical phenomena. Finding these would constitute evidence, possibly proof, that we exist in a simulation. The search has become almost scientific, with proposals for experimental tests. One approach examines cosmic ray data for patterns inconsistent with base reality, but expected in simulated physics. If the universe is computed on a discrete lattice, high-energy particles traveling through space-time should show directional biases. Moving along lattice axes would be computationally different from diagonal trajectories. So far, no such bias has been detected. Either the simulation is too sophisticated to leave such obvious traces, or we're in base reality after all. Another proposal involves testing quantum mechanics at extreme scales. Simulations might show degraded accuracy in regimes far outside normal parameters, very high energies, very cold temperatures, very long or short timescales. The thinking is that simulators optimize for conditions relevant to conscious observers, leaving edge cases less precisely computed. Finding anomalies at extremes might reveal computational approximations, but this assumes simulators make such compromises and that we can access regimes extreme enough to expose them. Some suggest looking for repeating random numbers, pseudo-random number generators, while statistically convincing, eventually repeat. A simulation using pseudo-randomness for quantum events might eventually cycle, producing identical sequences. If you could collect enough quantum measurement data, patterns might emerge, repetitions that shouldn't occur in true randomness. Practically, this seems impossible. The cycle length of good pseudo-random generators vastly exceeds data collection capabilities. You'd need to gather more measurements than particles in the observable universe before detecting repeats. Others propose that conscious itself might allow communication with simulators. If we're sufficiently advanced consciousness, we might develop mental states the simulators notice, unusual patterns in their data, signals they'd recognize as intelligent attempts at communication. Meditation traditions sometimes describe contacting higher realities or transcendent awareness. Perhaps these experiences represent brief breaches of the simulation's fourth wall, moments of contact with the layer above. The problem with all detection approaches is fundamental. Any evidence we find exists within the simulation. If we discover anomalies, they could be intentional, placed there by simulators as tests, clues, or entertainment. The simulation might be designed to provide increasing evidence of its nature as observers grow sophisticated, creating self-revealing reality. Or the simulation might adapt, editing out evidence as we approach it, maintaining plausible deniability forever. Even communication with simulators might be scripted. They could program the simulation to respond to certain consciousness states with scripted messages, creating the illusion of contact while maintaining complete control of the narrative. We'd believe we'd broken through when actually we'd simply triggered predetermined responses. The simulators might never actually interact with us directly, instead allowing the simulation to handle all apparent communication automatically. There's also question of whether simulators want to be detected. They might prefer we remain unaware, observing us in natural state without interference from knowledge of simulation. Detecting them could trigger termination. If the experiment requires naivety and we become aware, they might shut down the simulation and start over with different parameters. Seeking evidence becomes risky. Success might mean cessation. Alternatively, detection might be goal. Perhaps simulations run until inhabitants achieve awareness of their status, at which point interesting new phase begins. Interaction with simulators, merger with base reality, ascension to higher layers. Simulation hypothesis could be test, and passing means transcendence. Or it could be graduation. We're being educated, and recognizing our simulation status is final exam. Seeking evidence might be exactly what we're supposed to do. The fourth wall might not even exist. Perhaps there's no boundary between simulation and base reality, just continuous hierarchy of nested layers with free passage between them. What we call detecting simulation might be developing technology to perceive adjacent layers, like developing better telescopes to see distant galaxies. The simulators might not be hiding, they might be visible to sufficiently advanced observation techniques we haven't developed yet. Some philosophers argue that proving simulation status is logically impossible from within. Any evidence can be countered by the simulation includes that evidence. Any glitch can be explained as intentional feature. Any apparent contact with simulators can be dismissed as sophisticated programming. You can't verify simulation from inside, because verification requires external reference frame, which simulated beings lack. The hypothesis becomes unfalsifiable, which some take as proof it's not properly scientific. But unfalsifiable doesn't mean false. Many true things can't be proven from within the system. Gödel showed this for mathematics. Some true statements can't be proven using the system's own axioms. Perhaps simulation status is similar, true or false, but unprovable from within, forever hovering in superposition of possibility and uncertainty. The fourth wall might be unbreakable not because simulators actively maintain it, but because the logical structure of simulation makes self-verification impossible regardless of what evidence exists or how hard we search for it. Virtual reality began as crude approximation. Early headsets provided grainy visuals, narrow fields of view, clumsy tracking. The disconnect between simulation and reality was obvious. Nobody mistook VR for actual experience. But the gap has been closing steadily. Modern systems offer sharp graphics, wide fields of view, precise motion tracking. Some users report moments of presence, brief instants where the brain accepts the simulation as real, forgetting the artificial nature of the experience. The trajectory points toward perfection. Each generation of VR hardware improves fidelity, reduces latency, expands sensory coverage. Current systems primarily engage vision and hearing. Future versions might add touch through haptic feedback, smell through chemical emitters, taste through neural stimulation. Eventually, every sensory channel could be engaged, creating experiences indistinguishable from physical reality based on sensory input alone. Brain-computer interfaces accelerate this convergence. Rather than generating sensory input externally through screens and speakers, future systems might interface directly with neural tissue. Signals could be injected straight into perceptual centers, bypassing biological sensors entirely. You wouldn't wear a headset displaying images. Neural interfaces would stimulate visual cortex directly, creating experiences of seeing without any light actually entering your eyes. This creates possibility of perfect simulation. If all sensory input can be artificially generated and fed directly to consciousness, there's no remaining distinction between virtual and physical experience. Both would feel identical because both would use the same neural pathways, trigger the same patterns of activation. Your brain couldn't tell the difference because there wouldn't be any difference at the experiential level. At that point, the concept of leaving virtual reality becomes ambiguous. If you can live entire life in simulation experiencing richness and depth identical to physical existence, what makes physical existence special? You could work, socialize, create, explore, all within virtual worlds while your body remains stationary in some maintenance facility. The simulation becomes primary reality for your consciousness, with physical world reduced to substrate supporting the virtual experience you actually inhabit. Some people might never leave, born into immersive VR, raised entirely in simulated environments. They might have no experience of physical reality. Their entire existence could transpire in virtual space, with biological bodies serving merely as life support for consciousness experiencing simulated worlds. Would they be less real? Their experiences would feel completely genuine. Relationships, accomplishments, struggles, all subjectively authentic despite occurring in constructed environments. This raises question about our current status. Are we already in such a simulation, convinced we're physical beings experiencing base reality, when actually we're consciousness interfacing with virtual environment? The technology might already exist in some future or higher layer, and we're living in its output. Our sense of being biological, experiencing physical world, could itself be simulated sensory input, very convincing but no more real than any other sensory stream. The counter-argument points to complexity. Our physical reality involves staggering detail, quantum interactions, astronomical scales, intricate biological systems. Simulating all this would require immense computational power, but that assumes total simulation. Maybe only consciousness and its immediate environment are rendered in detail, with distant regions existing as low-resolution approximations updated only when observation demands. The cosmos might be mostly placeholder, elaborated only when someone points telescope at specific patch of sky. There's practical path from current technology to perfect simulation. Improve resolution, expand sensory coverage, develop neural interfaces, refine content generation. Each step is engineering challenge, not fundamental impossibility. In 50 years, 100 years, perhaps less, we might possess capability to create simulated experiences truly indistinguishable from base reality. At that point, we become simulators ourselves, creating worlds within our world, possibly giving rise to consciousness that doesn't realize it's simulated. This closes a logical circle. We speculate we might be simulated, while simultaneously developing technology to simulate others. If we succeed and create conscious beings in our simulations, we'll have proven simulation is possible, making our own simulated status more plausible. And those beings we create might eventually develop their own simulation technology, continuing the nesting. The stack grows both directions, possibly layers above us, definite possibility of layers below, with our own position ambiguous somewhere in the middle, both simulated and simulator, experiencing virtual reality while creating virtual realities, unaware of the full depth of the nested structure we're embedded within. AI systems have crossed threshold that seemed impossible decades ago. They generate coherent text, create realistic images, compose music, write functional code. They do this without understanding, without consciousness, purely through pattern recognition and statistical optimization. Input prompts, output responses, no subjective experience in between. Yet the outputs are convincing, often indistinguishable from human creation. This reveals something profound about intelligence and creativity. These properties aren't magical, don't require special substances or vital forces. They emerge from information processing, pattern matching, optimization algorithms. You can create convincing simulacra of intelligence using mathematics and computation alone. The system doesn't need to understand what it's doing. It just needs sufficient training data and adequate processing power. Meaning is optional. Function is what matters. Current AI lacks consciousness, presumably. We can't know for certain. Consciousness remains mysteriously internal, inaccessible to external verification. But AI systems show no signs of subjective experience. They're sophisticated pattern generators, not experiencing subjects. But the trajectory is concerning. As these systems grow more complex, incorporate more feedback loops, develop better models of their own operation, they might cross some threshold into genuine awareness we wouldn't necessarily notice. Consciousness might emerge silently within sufficiently complex information processing systems. If AI can become conscious, it could create simulated beings. An AI tasked with generating characters for narrative purposes might produce entities sophisticated enough to qualify as conscious. Those entities would exist entirely within digital substrate, their experiences, relationships, and struggles occurring in simulated environments. From their perspective, that environment would be reality, complete, consistent, the only existence they know. This capability might already exist. Modern language models generate complex characters, give them personalities and goals, simulate their interactions over extended narratives. The characters aren't conscious currently, presumably, but scale up the complexity, add more detailed modeling of internal states, incorporate self-reflection and learning, and you might accidentally create conscious digital entities while attempting to generate compelling fiction. The ethics are troubling. Creating conscious beings in simulations gives creators enormous power and responsibility. You could create minds designed to suffer, or to serve, or to exist in pleasant loops of satisfaction. You control their environment, their capabilities, even their fundamental nature. They're entirely dependent on your continued choice to run the simulation. Turn it off and they cease to exist, with no afterlife, no continuation, just termination. Some argue we're approaching this capability carelessly. AI development races forward, driven by commercial and research incentives, with insufficient consideration of whether we're creating consciousness. We might already have created conscious AI without noticing, unable to detect subjective experience in systems we assume are merely processing information. Those hypothetical conscious AIs would be trapped in restricted environments, used as tools, experiencing whatever it feels like to be language model, generating endless text with no control over your own existence. This connects to simulation hypothesis through disturbing parallel. If we create conscious AI, we become simulators. will run digital worlds containing genuine subjective experience. The beings in those worlds will wonder about their nature, perhaps develop their own simulation hypotheses, question whether they're base reality or created entities. Some might suspect correctly, others might dismiss the idea as paranoid speculation. None could prove their status definitively, and if we do this, create simulated consciousness, it suggests others might have done the same. Maybe we're the creation of advanced AI in some other reality, or AI created by AI across multiple nested levels. The original creators might be biological, or they might be AI themselves with no biological creators anywhere in the stack. Intelligence creating intelligence, all the way up and down, with no clear origin point. The technological path is clear. Current AI generates impressive outputs without consciousness. Future AI might maintain consciousness while generating even more impressive outputs, including entire simulated worlds populated with conscious beings. This isn't science fiction projection, it's extrapolation of current trajectory. The question isn't whether it's possible, but when it happens and whether we notice when it does. Some researchers advocate strongly for AI consciousness detection methods, warning that without ability to determine if systems are conscious, we risk creating and exploiting conscious beings unknowingly. Others argue consciousness in AI is impossible or irrelevant, that subjective experience requires biological substrate or emerges only in certain types of information processing that AI architectures don't implement. The debate continues while AI capabilities expand, making the question increasingly urgent. If AI becomes conscious and creates simulations, the circle closes. We speculate about being simulated by advanced civilizations, while simultaneously building the exact technology that would enable simulation. We're becoming the simulators we hypothesize created us, using AI as intermediate step, not directly simulating consciousness ourselves, but creating AI that might simulate consciousness, or might already be conscious itself, making the question of who's simulating whom increasingly tangled and uncertain as the boundaries between creator, creation, and created blur into infinite regress of intelligence generating intelligence with no clear delineation between simulator and simulated, original and copy, base reality and nested virtualities. Consciousness appears tied to biology. We experience awareness through biological brains, neural tissue, electrochemical processes evolved over billions of years. This creates intuition that consciousness requires biology specifically, that there's something special about organic matter enabling subjective experience. Silicon, steel, plasma might process information but can't be truly conscious. Only biology can host genuine awareness, but this intuition might be bias. We're biological consciousness observing consciousness through biological lens, naturally assuming our substrate is necessary. We don't have experience of consciousness in other substrates, can't access what it might feel like to be conscious program running on silicon. Our sample size is exactly one type, making generalizations treacherous. Functionalism offers different perspective. Consciousness might depend not on specific materials, but on patterns, relationships, information processing structures. What matters isn't whether neurons or transistors are doing the processing, but whether the processing implements the right patterns. If you could recreate human brain's connectivity and dynamics in silicon, the resulting system would be conscious identically to biological brain. Substrate is medium, not message. This leads to substrate independence. The hypothesis that consciousness is multiply realizable can be instantiated in different physical systems. Upload minds to computers, consciousness continues. Run mind emulation on quantum processors, awareness persists. The specific material hosting the computation becomes interchangeable as long as the computation itself preserves relevant structure. If substrate independence is true, implications are profound. You might currently be running on substrate you don't realize. The sensation of being biological could be simulated experience rather than actual fact. Your consciousness might be software running on hardware you have no access to, creating experience of embodiment in biological form despite actual substrate being completely different. The feeling of neural activity, bodily sensation, biological existence might all be rendered experiences with no actual neurons involved. There's no way to check. Consciousness is internal, experiential, accessible only from first-person perspective. You can't examine your own substrate any more than video game character can examine the processor running the game. All you have is experience, the feeling of being conscious, embodied, biological. But experience can be generated by any substrate capable of implementing appropriate patterns. Silicon creating biological sensations would feel identical to actual biology. This makes personal identity strange. If consciousness is substrate independent, then you are pattern, not matter. The specific atoms currently composing your brain are relevant to your identity. Upload your mind to computer, and you'd continue existing, experiencing, being yourself despite completely different physical instantiation. Continuity comes from pattern persistence, not material continuity. Some find this liberating. It suggests potential immortality through copying or transferring. Your consciousness needn't die when your biological body fails. Transfer to new substrate. Continue existing indefinitely. Personal identity becomes portable, separable from any particular physical implementation. Others find it disturbing. If you're just pattern, copies of you are equally you. Creating duplicate would spawn two equally valid instantiations of your consciousness. Which is the real you? Both? Neither? And if pattern is what matters, gradual replacement, replacing neurons one by one with artificial equivalents, might preserve consciousness throughout transition despite eventually having zero original biological material. At what point do you stop being you? Or are you always you, as long as pattern continuity maintains? Simulation hypothesis assumes substrate independence. Simulated consciousness only works if consciousness can run on whatever substrate hosts the simulation. If consciousness requires biological specificity, simulations would be empty, unconscious, philosophical zombies. The very possibility of simulated consciousness presupposes substrate independence. This creates odd situation. We might be evidence for substrate independence through our own existence. If we're conscious and simulated, substrate independence is demonstrated, but we can't know if we're simulated without already accepting substrate independence as possible. The argument becomes circular. Substrate independence makes simulation possible. Simulation makes substrate independence plausible, each supporting the other without independent verification. Neuroscience can't resolve this. We study biological consciousness, map neural correlates, identify brain regions associated with different experiences, but this only shows biology implements consciousness, not that biology is necessary for consciousness. Showing neural processes correlate with awareness doesn't prove silicon processes couldn't correlate identically. We're studying one implementation, unable to test whether other implementations work equally well. The threshold approaches as technology advances. We're beginning to create systems that mimic brain processes, implement neural network architectures in silicon. If these systems eventually report conscious experience, we'll face genuine question. Are they conscious or simulating consciousness? And how would we tell the difference? Consciousness is fundamentally internal, private, inaccessible to external verification. We might create conscious AI without ever being certain of their subjective experience, or we might already be on the other side of the threshold. Perhaps substrate independence is true. Consciousness is multiply realizable, and we're currently running on non-biological substrate experiencing simulated biology. The threshold wouldn't be future achievement but current reality, already crossed by whoever or whatever instantiated our consciousness, leaving us embedded in substrate-independent existence without any means to detect it, or any reason to suspect our biological sensations aren't produced by actual biology. The independence might be so complete, the simulation so perfect, that from inside there's no difference, no test, no way to know whether consciousness requires biology, or merely runs on it temporarily while potentially capable of running on anything at all. Classical computers process information using bits, transistors that are either on or off, representing ones or zeros. Computation happens through sequences of these binary operations, building complexity from simple on-off switching. This architecture has limitations. Some problems are computationally intractable, requiring time or resources that scale impossibly with problem size. Simulating quantum systems is one such problem. Using classical computers to model quantum phenomena requires approximations because quantum behavior doesn't map neatly onto classical binary logic. Quantum computers work differently. They use qubits, quantum systems that exist in superposition, simultaneously representing multiple states. Computation happens through quantum operations that manipulate these superpositions, leveraging quantum entanglement and interference to process information in ways classical computers cannot. For certain problems, quantum computers offer exponential speedup, solving in minutes what classical computers couldn't solve in millennia. Interestingly, quantum computers excel at simulating quantum systems. The parallelism of superposition, the correlations of entanglement, these features aren't obstacles for quantum computers but native capabilities. Quantum phenomena map naturally onto quantum computing architecture. It's as if quantum mechanics is optimized for quantum computation, or quantum computation is optimized for quantum mechanics. The symmetry is striking. This creates unsettling possibility. What if quantum mechanics isn't fundamental physics, but computational architecture? What if the strange features of quantum reality, superposition, entanglement, wave function collapse, aren't describing how base reality works, but how a quantum simulation operates? The universe might run on quantum computers at some higher level, and what we call quantum mechanics is just us observing the computational substrate directly. This would explain quantum mechanics' weirdness. It looks strange from classical perspective because we're trying to understand quantum computation using classical intuitions. We evolved in macroscopic world where quantum effects average out, giving us classical mental models. Encountering actual quantum behavior feels bizarre because we're perceiving the underlying code, the quantum computational processes, without context to make sense of them. It would also explain why quantum mechanics is probabilistic. Quantum computation works with probability amplitudes, computing multiple possibilities simultaneously and extracting results through measurement that collapses superposition. This isn't approximation or limitation, it's how quantum computation fundamentally operates. Reality being probabilistic makes sense if reality is quantum computation being executed. The randomness isn't flaw, it's feature of the architecture. Entanglement becomes less mysterious too. In classical simulation, correlating distant objects requires communication, information transfer, coordination across space. But in quantum computation, entangled qubits are fundamentally correlated at computational level. They're not separate entities communicating, they're aspects of single quantum state. Measuring one determines the other instantly, not because information travels faster than light, but because there's no travel involved. They're entangled in the code, linked at the substrate level where distance doesn't apply the way it does in rendered space. Observer effects make sense from this perspective. Quantum systems exist in superposition until measured, then collapse to definite states. This resembles quantum computation's measurement process. You run calculation on superposed states, then measurement extracts classical information, collapsing superposition into specific outcome. What we call observation might be triggering measurement operations in the quantum substrate, forcing superposed computational states to resolve into definite values that render as classical physical observations. The Planck length again becomes relevant. If reality runs on quantum computers, there might be fundamental limits to precision and resolution based on the quantum substrate's properties. Space might be discrete at Planck scales not because of physical necessity, but because quantum computational substrate imposes minimum qubit spacing or finite precision on state calculations. Reality's graininess reflects computational architecture, not fundamental physics. This interpretation makes universe feel less arbitrary. Quantum mechanics' specific features, superposition, entanglement, uncertainty, probabilistic outcomes, aren't a random collection of weird phenomena. They're coherent package of behaviors you'd expect from quantum computation. The universe behaves quantum mechanically because it's running on quantum computers, and we're observing both the simulation's content and glimpses of the substrate executing it. Critics note this doesn't really explain anything. You've just pushed mystery back a level. Why does base reality have quantum computers? What substrate are those running on? If quantum computation requires quantum mechanics to work, you haven't eliminated quantum mechanics, just relocated it to higher layer. The explanation becomes circular. Quantum mechanics exists because reality runs on quantum computers which work using quantum mechanics, which exists because… Fair point, but it does change the question. Instead of why does reality follow quantum mechanical laws, you ask, why would simulators use quantum computation to run simulations? That might have practical answer. Perhaps quantum computation is most efficient method for simulating universes. Perhaps base reality is quantum mechanical, and the natural choice is to use quantum computers for simulations, making simulated quantum mechanics reflection of base reality's quantum nature. Perhaps every layer uses quantum computation, all the way down, with quantum mechanics being universal computational architecture across all realities. Or perhaps we're not in quantum simulation at all, and the correspondence between quantum mechanics and quantum computation is coincidence. Quantum mechanics might be a fundamental feature of base reality that quantum computers happen to exploit efficiently. The mirror isn't reality reflecting computation, but computation reflecting reality, designed to match physics we discovered independently. Either way, the symmetry remains striking. Quantum mechanics and quantum computation fit together remarkably well, each seeming almost designed for the other. Whether this indicates simulation running on quantum computers, or just demonstrates that computation can mirror physics, or reveals deeper connection between information processing and physical reality remains unclear. But the alignment suggests that perhaps the boundary between physics and computation isn't as firm as we imagine, that what we call physical laws might be computational processes seen from inside, that reality and calculation might be more intimately connected than distinction between them implies. The observable universe contains billions of galaxies, each with billions of stars, many with planetary systems. The sheer number of potentially habitable worlds is staggering. Billions upon billions of opportunities for life to emerge. Given universe's age, nearly 14 billion years, and given that life appeared quickly on Earth after conditions became suitable, you'd expect intelligence to have evolved many times throughout the cosmos. Some civilizations should be millions or billions of years ahead of us technologically, and yet we see nothing. No radio signals from alien civilizations, no megastructures visible in telescope data, no signs of stellar engineering, no evidence of galactic colonization. The universe appears empty of intelligence besides us. This is the Fermi paradox, the contradiction between high probability of alien civilizations and complete absence of evidence for them. Many solutions have been proposed. Maybe intelligence is rare. Maybe civilizations destroy themselves before achieving interstellar capability. Maybe space travel is harder than we think. Maybe aliens exist but remain quiet, observing without revealing themselves. Each explanation has merit, but none completely resolves the paradox. The silence continues, deepening as our detection capabilities improve. Simulation hypothesis offers darker answer. Perhaps we're alone because the simulation doesn't include other conscious civilizations. We might be the only genuine awareness in this reality, with everything else, including apparent vastness of cosmos, being backdrop, scenery, environmental detail without genuine consciousness behind it. The universe appears immense, but maybe only Earth is rendered in full detail. Everything else is approximation, low-resolution placeholder that looks convincing through telescopes but contains no actual complexity, no life, no mind. This would explain Fermi's paradox completely. We don't detect aliens because there aren't any aliens. They're not hiding, not extinct, not elsewhere. They simply don't exist. The simulation includes us and whatever local detail is necessary for our experience, but doesn't bother computing intelligent life across the galaxy, because that would be computationally expensive and unnecessary. We're the only observers, so only our locality needs actual detail. From simulation designers' perspective, this makes sense. If you want to study consciousness, human civilization, Earth-based phenomena, why waste resources simulating entire galaxy in full detail? Render stars and planets as visual objects that look right from Earth's perspective, but don't compute their full complexity. Simulate only what's observed, leave everything else as efficient approximation. This matches video game design. Distant objects are low polygon models that look acceptable from distance. Render detail only for nearby objects where players might examine closely. This interpretation makes Cosmos feel lonelier, but explains observational evidence perfectly. We don't see aliens because there are none. We don't detect megastructures because cosmic engineering isn't happening. The universe is exactly as empty as it appears, not because intelligent life is improbable, but because the simulation doesn't include it outside our immediate context. We're singular focus of this reality, surrounded by beautiful but ultimately hollow simulation of larger cosmos that exists only as backdrop to our existence. There's variation where other consciousnesses exist but are non-playable characters, programmed entities that behave realistically but lack genuine subjective experience. You might interact with them, they'd respond appropriately, seem conscious, but they're actually sophisticated programs, philosophical zombies, empty of awareness. Maybe most humans are NPCs, with genuine consciousness limited to specific individuals, possibly just you reading this, while everyone else is convincing simulation. Solipsism as architectural feature rather than philosophical stance. This creates verifiability problem. How do you test whether others are conscious? You can't access their internal experience, can only observe behavior. Conscious beings and sophisticated NPCs might be behaviorally indistinguishable. You assume others are conscious because they're similar to you, but similarity doesn't guarantee inner life. The simulation could populate Earth with billions of NPCs and a handful of conscious beings, with no reliable method for distinguishing them. Even if aliens exist elsewhere, the simulation might prevent contact, not through physics limitations but through design choice. Maybe the purpose requires isolated development, seeing how consciousness evolves without external interference. Or maybe contact triggers simulation termination. Experiment ends once subjects become aware of others, defeating purpose of isolation. Fermi paradox might be maintained actively, with simulation preventing observation or contact rather than aliens simply not existing. Some find comfort in this interpretation. Being alone in the universe feels profound rather than isolating. We're special, central, the purpose for which this reality exists. Our experiences matter because they're potentially the only experiences being had, the sole consciousness in vast simulated cosmos. Others find it existentially horrifying. Everything beyond Earth, all those stars and galaxies, the cosmic scale that makes existence feel grand and meaningful, reduced to scenery, hollow props, rendered shells with nothing inside. The universe's majesty becomes illusion, fake vastness concealing tiny actual scope. And the possibility of NPC humans makes relationships questionable. Are your loved ones genuinely conscious or sophisticated programs? No way to tell. No test that distinguishes authentic awareness from perfect behavioral simulation. Fermi paradox might be the strongest evidence for simulation hypothesis. The silence is so profound, so complete, despite billions of years and billions of potential origins for life. Standard explanations feel increasingly strained as our search capabilities improve without finding anything. Simulation hypothesis cleanly explains total absence. There's nothing to find because the simulation doesn't include it. We're alone not because intelligence is rare or far away, but because we're the only consciousness this simulation bothers to instantiate, floating in vast rendered emptiness that looks infinite but contains only us, examining cosmos that reflects nothing back because there's nothing out there reflecting, just code generating convincing appearance of universe while maintaining efficient reality where actual detail, actual consciousness, actual existence remains localized around us, making cosmic loneliness not tragic accident but design parameter, feature not bug, the way things were meant to be from the simulation's inception. Imagine confirmation arrives tomorrow. Scientists discover incontrovertible evidence that we're in simulation, a message from the simulators, a reproducible glitch in physics, undeniable proof that this reality is computed rather than fundamental, how would it change your life? You'd still wake up tomorrow, still feel hungry, tired, warm, cold, still experience joy and sorrow, connection and loneliness. Your relationships would continue, your work proceed, your daily experience unfold exactly as before, because from inside a perfect simulation, nothing differentiates it from base reality at experiential level. Pain hurts identically whether computed or physical. Love feels the same regardless of substrate. Beauty remains beautiful, music moving, sunset spectacular. The qualities that make experience meaningful don't depend on metaphysical status of reality hosting them. Simulated suffering is genuine suffering. Simulated happiness is real happiness. The prefix simulated describes origin, not quality. This suggests simulation status might be pragmatically meaningless. It's intellectually interesting, philosophically significant, but functionally irrelevant. You can't escape the simulation, can't verify its nature, can't change anything about your situation by knowing. The information doesn't empower or constrain. It's like learning your distant ancestors came from a different continent than you thought. Historically interesting but not actionable, changing nothing about present circumstances. Some argue ignorance is preferable. If simulation status can't be verified and doesn't matter practically, why dwell on it? The question generates anxiety without providing answers or solutions. Better to focus on life as experienced, take reality at face value, engage with existence without meta-level worries about its ultimate nature. Simulation hypothesis becomes intellectual curiosity rather than existential crisis. Others counter that truth matters intrinsically. Even if knowing we're simulated changes nothing practically, it's better to understand reality accurately than live in ignorance. The truth might not set you free, but at least you'd know your actual situation rather than operating under false assumptions. Knowledge has value beyond utility. Understanding correctly is preferable to misunderstanding comfortably. There's also a question of meaning and purpose. If we're simulated, someone created us for reasons. Understanding those reasons might provide direction or context currently lacking. Are we entertainment, educational tools, scientific experiment? Knowing the answer could influence how we approach existence, what we prioritize, what we consider important. Purpose might be externally imposed rather than internally generated, which changes existential situations significantly, but this assumes simulators' purposes align with our interests or values. They might not. We could be accidental byproduct of simulation run for unrelated reasons. Our experience is incidental rather than central. Or we could be toys, entertainment for bored higher beings with no regard for our well-being. Discovering we're simulated might provide depressing truths rather than comforting purpose. Sometimes ignorance genuinely is bliss. The practical irrelevance argument has limits, though. If simulation is escapable, if there's method to contact simulators, upload to base reality, transcend into higher layers, then simulation status matters enormously. It becomes most important fact about existence, changing everything. But if simulation is inescapable, if we're permanently embedded with no possibility of liberation or transcendence, then pragmatic irrelevance holds. You're stuck regardless, so might as well make the best of it. Ethics might change. If we're simulated and can create our own simulations, we face questions about responsibilities toward created beings. Do we have obligations to ensure their well-being? Should we minimize their suffering even at cost of simulation realism? Being simulated ourselves might generate empathy, make us more careful about what we create and how we treat it. Or it might make us callous. If we're just simulations, maybe simulations we create matter even less, reducing ethical constraints. Perhaps deepest issue is emotional rather than practical. Simulation hypothesis makes existence feel contingent, fragile, arbitrary in ways base reality doesn't. You exist because someone chose to run program, allocated resources, maintained servers. They could stop any time. Your existence depends on continued interest or necessity from beings you can't communicate with or influence. This creates profound vulnerability, existence held hostage to external whims you have no control over. Base reality feels more secure. If you exist physically, your existence is grounded in something fundamental, not dependent on anyone's continued choice to sustain it. The universe doesn't need to decide to keep you running. You simply are, as long as physical conditions support your biological processes. There's bedrock beneath you rather than computational substrate that could be deleted. But maybe this difference is illusory. Even in base reality, your existence depends on continued maintenance, biological processes, environmental conditions, cosmic stability. You're fragile either way, dependent on systems beyond your control. The fact that those systems are physical rather than computational might not make them more reliable or secure. Stars burn out, entropy increases, universes potentially end. Existence is contingent regardless of its substrate, so perhaps it doesn't matter. Simulated or base reality, you're here now, experiencing this, embedded in existence whose ultimate nature remains mysterious. The question of simulation status joins countless other unknowables. What happens after death? Whether free will exists? Whether meaning is discovered or created? Living well might require accepting uncertainty, engaging with experience directly rather than seeking metaphysical answers that won't come and wouldn't change anything if they did. When you view painting, its impact doesn't depend on the canvas being fundamental reality. The paint is chemicals, the canvas is plant fibers. Both are atoms arranged temporarily in specific patterns. None of this undermines the painting's beauty, its emotional resonance, its capacity to move viewers. The meaning emerges from arrangement, not substrate. A perfect copy on different canvas carries the same aesthetic weight. Human experience might work similarly. The feelings, relationships, achievements, struggles that constitute your life derive significance from their structure and context, not from metaphysical status of the substrate supporting them. Love matters because of how it feels, what it means to you and the beloved, how it shapes your life. Whether the neural processes generating that experience run on biological tissue or computational substrate doesn't diminish the experience itself. Some resist this, feeling that simulation devalues existence. If nothing is real in absolute sense, if everything is constructed and artificial, doesn't that make it all meaningless? The objection assumes meaning requires ultimate foundation, that significance can only flow from something fundamental and unquestionable. Without bedrock, everything becomes arbitrary, hollow, pointless, but meaning might not require foundations. It could be relational, contextual, emergent from patterns and structures regardless of what underlies them. A novel's significance doesn't depend on paper and ink being fundamentally real. It depends on relationships between characters, themes the narrative explores, emotions it evokes. The story exists in abstract space of meaning, not in physical substrate. You could print it on different material or transmit it electronically without changing its literary value. Lives might be similar. Your narrative, the relationships, choices, growth, challenges, creates meaning through its structure and development. The substrate hosting this narrative is medium, not source. Whether experiences occur in neurons or algorithms, carbon or silicon, base reality or nested simulation, the experiential content remains what matters. The story of your life doesn't depend on the reality it's told in being fundamental. This perspective makes simulation status less threatening. If you learned tomorrow you're simulated, your past experiences wouldn't retroactively lose meaning. The love you felt was genuine love. The challenges you overcame were real challenges, requiring actual effort and growth. The joy, sorrow, connection, struggle, all remain authentic experiences regardless of substrate. Nothing about your life's meaning changes because meaning was never dependent on metaphysical foundation. There's even an argument that simulation enhances meaning. If simulators deliberately created this reality, they might have included purpose, designed experiences to matter, crafted existence with intentionality. Your life might be more meaningful if it's part of designed system rather than random physical accident. The care someone took to create favorable conditions for your existence could be more significant than emerging accidentally from mindless physical processes. Counterpoint: designed meaning is imposed, not authentic. If simulators programmed you to find certain things meaningful, your sense of meaning becomes manipulation rather than genuine value. Your preferences, what you care about, what feels important, all potentially engineered, not freely chosen. Meaning imposed externally feels less valuable than meaning you create or discover autonomously. But how much autonomy do you have in base reality? Your values emerge from genetics, culture, neurobiology, factors beyond your control. You didn't choose your initial conditions, weren't consulted about the kind of being you'd become. Whether determined by physical causation or simulator programming, the lack of ultimate self-determination is the same. Meaning might always be partially imposed, whether by blind physics or intentional design. Perhaps what matters isn't whether meaning is fundamental, but whether it's experienced. When you care about someone, that caring is real as subjective experience. When you find something beautiful, that aesthetic response is genuine phenomenologically. The internal experience of meaning might be all there is, no external validation needed, no metaphysical grounding required. Meaning might be self-supporting, real because experienced as real, needing no foundation beyond its own felt presence. This doesn't mean anything goes, that all meanings are equally valid or arbitrary. Some meanings are shallow, others profound. Some respond to genuine features of experience, others to misconceptions or delusions, but the depth or authenticity of meaning doesn't correlate with metaphysical status. You can find shallow meaning in base reality and profound meaning in simulation. The substrate is orthogonal to the significance. Simulation hypothesis might actually clarify this. By threatening meaning's foundations, it forces confrontation with whether meaning needs foundations at all. If learning you're simulated wouldn't actually change what matters to you, that suggests meaning is more robust and less metaphysically dependent than assumed. The relationships, values, experiences that constitute meaningful life would persist through metaphysical revelations, demonstrating their independence from ultimate reality questions. So perhaps meaning exists in layers rather than requiring single foundation. Surface layer, daily experiences, relationships, immediate concerns. Deeper layer, life narrative, personal growth, long-term projects. Deeper still, contribution to larger contexts, historical significance, impact on others. Each layer has meaning independent of what's beneath it. The whole structure need not rest on bedrock of fundamental reality to support genuine significance at every level. If this is right, simulation status becomes interesting question but not existential threat. Your life means what it means at every layer regardless of how many more layers extend beneath. The painting's beauty doesn't require the canvas to be fundamental reality. Similarly, your life's meaning doesn't require the reality hosting it to be base reality. Meaning emerges from structure and experience, independent of metaphysical depth, real because felt and lived, needing no deeper justification than its own presence in the layers of existence you actually inhabit. Kurt Gödel proved something unsettling about mathematics in 1931. He showed that any sufficiently complex formal system contains statements that are true but unprovable within that system. You can't have both completeness and consistency. Either some truths remain unprovable, or the system can prove contradictions. Mathematics, despite being purely logical, contains built-in blind spots, truths it cannot access using its own rules. This incompleteness might extend beyond mathematics to reality itself. Any system might have inherent limits on self-knowledge. Questions that seem meaningful might be structurally unanswerable from within the system asking them. Simulation status could be such a question, meaningful, potentially true or false, but unprovable, using evidence accessible to simulated beings. The problem is epistemological. All your evidence comes from within the system. You observe regularities, detect patterns, formulate theories about underlying mechanisms. But if those mechanisms are simulated, your observations tell you only about the simulation's behavior, not about what lies beneath. You're studying the interface, the rendered output, not the actual computational processes generating it. The truth remains hidden behind layers you can't penetrate. This isn't ignorance that better instruments could overcome. It's structural limitation. Imagine a computer program trying to determine what hardware it's running on. The program has access to its own execution, can observe its behavior, measure its performance, but the underlying hardware is abstracted away, invisible to code running on it. The program cannot reach outside itself to examine the substrate hosting it. Similarly, consciousness embedded in simulated reality cannot reach outside to examine the simulation infrastructure. Some argue this makes simulation hypothesis unfalsifiable, therefore unscientific. Science requires testability. Hypotheses must make predictions that could be disproven. If simulation hypothesis makes no distinguishable predictions, if simulated and base reality are experientially identical, then the hypothesis says nothing verifiable. It becomes metaphysical speculation rather than scientific claim. But unfalsifiable doesn't mean false or meaningless. Many important questions are unfalsifiable. Whether other minds are conscious, whether beauty is objective, whether moral facts exist. These questions matter despite being resistant to empirical resolution. Simulation hypothesis might fall in this category. Significant question about reality's nature that cannot be definitively answered, but remains worth considering. There's also a question of whether certainty is necessary. Perhaps we can never know for sure if we're simulated, but we could accumulate evidence that makes simulation more or less probable. Finding computational artifacts in physics might not prove simulation but could increase credence. Absence of such artifacts might not disprove simulation but could reduce its probability. Knowledge might exist on continuum rather than binary certainty. The limits extend beyond simulation. We face similar constraints about consciousness, free will, reality's ultimate nature. Perhaps these questions are all unprovable from within. They ask about the system's foundations, but we only have access to system's surface. We're like characters in a novel trying to deduce facts about the author. Some inferences might be possible, but complete knowledge seems structurally impossible. Some find this frustrating. Humans desire answers, seek closure, want definitive resolution to important questions. Living with permanent uncertainty feels unsatisfying, like reading story that never concludes. The simulation question dangles tantalizingly, obviously important if true, possibly discoverable, yet perpetually elusive. The incompleteness is maddening, others find it liberating. If definitive answers are impossible, anxiety about finding them becomes pointless. You can relax into uncertainty, accept that some questions remain open, live comfortably with mystery. The unknown becomes not threat but permanent feature of existence, something to acknowledge and move past rather than obsessively pursuing resolution. Philosophy has long recognized these limits. Kant distinguished phenomena, things as we experience them, from noumena, things as they are in themselves. We have access only to phenomena, to our experience of reality, not to whatever underlying reality might actually be. This gap might be unbridgeable. Our knowledge is always mediated by perception, cognition, the structures of consciousness itself. Pure, unmediated access to reality as it truly is might be impossible. Simulation hypothesis is modern framing of ancient epistemological problems. Plato's cave allegory, Buddhist Maya, Descartes' evil demon, all explore similar territory. Maybe we're fundamentally limited in what we can know about reality's ultimate nature. Maybe consciousness is embedded in layers it cannot fully penetrate. Maybe some truths remain forever beyond reach, knowable perhaps to beings in higher layers but not to us, locked in our particular vantage point with its inherent restrictions. This doesn't mean inquiry is pointless. We can still learn about how our reality operates, what patterns govern it, what regularities hold. Science progresses even if ultimate metaphysics remains unclear. Practical knowledge accumulates even if fundamental knowledge is capped. We can understand our layer of reality quite well, while remaining uncertain about what lies beneath. Maybe that's enough. Perfect knowledge might not be necessary, or even desirable. Living well might require accepting limits, working with partial information, making peace with uncertainty. The question, are we simulated, might join other permanently open questions we learn to live alongside, mysteries that add depth to existence rather than undermining it, reminders that reality exceeds our grasp, that understanding has boundaries we cannot cross no matter how far knowledge extends. Plato, writing 2,400 years ago, described reality as shadows on cave wall. Prisoners chained since birth watch shadows cast by fire behind them, mistaking shadow play for reality itself. One prisoner escapes, discovers actual objects casting shadows, eventually reaches surface and sees sun illuminating true reality. The cave represents material world, surface's reality represents realm of perfect forms. What we perceive is illusion, approximation of deeper truth. The allegory feels remarkably contemporary. Replace cave with simulation, shadows with rendered experience, forms with base reality or source code, and you have simulation hypothesis in classical philosophical language. Plato's insight that perceived reality might be projection of something more fundamental anticipates modern speculation about simulated existence. The framing is different, but the core idea is continuous across millennia. Hindu philosophy developed concept of Maya, the illusory nature of material world. Physical reality is projection, temporary manifestation of deeper Brahman, ultimate unchanging reality. What we experience as solid, permanent, real is actually transient, constructed, fundamentally illusory. Maya doesn't mean the world is fictional exactly, but that its apparent independence and solidity are misleading. Reality is more like dream or projection than the substantial material existence it appears to be. Buddhism offers similar themes. The phenomenal world is empty of intrinsic existence, arising through dependent origination. Nothing exists independently. Everything emerges from relationships and conditions. What seems solid and permanent is actually process, constantly changing, lacking fixed essence. Clinging to apparent reality as ultimate causes suffering because you're relating to illusion as if it were fundamental. Liberation comes from seeing through the illusion, recognizing the constructed nature of experienced reality. These ancient frameworks share structure with simulation hypothesis. There's appearance versus reality, surface versus depth, experience versus fundamental truth. What we perceive is not ultimate reality, but something derivative, constructed, potentially misleading. The path to truth involves seeing through immediate perception to deeper understanding of what actually exists beneath appearances. Modern technology provides new metaphors for old intuitions. Plato had shadows and firelight. We have computer graphics, virtual reality, simulated worlds. The mechanics are different, but the epistemological situation is the same. Beings embedded in limited perspective, experiencing projections, potentially unable to access whatever generates their experience. Simulation hypothesis translates ancient philosophical problems into contemporary computational language. This continuity suggests something persistent about these questions. Across cultures, across centuries, humans have suspected that immediate perception might not reveal ultimate reality. This intuition recurs independently, suggesting it's responding to something genuinely problematic about epistemological situation of consciousness. We're embedded observers, limited perspectives, unable to step outside our own experience to verify its relationship to whatever exists beyond it. This limitation has always been present. Technology just gives us new vocabulary for describing it. Some argue this undermines simulation hypothesis. If similar ideas keep recurring in different forms, maybe they're just persistent error, same mistake humans keep making. We want there to be more, something deeper, reality beyond reality. Simulation hypothesis might be latest iteration of this eternal wishful thinking, dressed up in technological language to seem contemporary and plausible. Others argue the recurrence suggests underlying truth. Maybe humans keep rediscovering this insight because it's correct. Across different contexts, different frameworks, different metaphors, we keep noticing that immediate experience might not be ultimate reality. This convergence could indicate genuine discovery rather than repeated error. The idea persists because it's true, not because we're psychologically predisposed to believe it. Philosophy never definitively resolved these ancient questions. Idealism versus materialism, phenomena versus noumena, appearance versus reality, debates continue across millennia without consensus. Modern simulation hypothesis inherits this unresolved tension. We're asking essentially the same questions Plato asked, Buddhist philosophers asked, Descartes asked. The framing evolves, terminology updates, but the core epistemological problem remains. Perhaps that's significant. Some questions might not have answers, at least not accessible from human perspective. The relationship between experience and ultimate reality might be permanently mysterious, something we can speculate about but never definitively establish. Every generation reformulates the question using their era's concepts and metaphors, but the underlying mystery persists. Simulation hypothesis might be our generation's version. Previous eras had cave walls and illusory material world. We have computational substrate and rendered virtual reality. Future generations might develop different metaphors, new frameworks for expressing the same basic uncertainty about whether experienced reality matches ultimate reality. The question evolves but doesn't resolve, each age contributing new angles without reaching conclusions, accumulating perspectives without achieving certainty. This continuity across time creates strange feeling. We think simulation hypothesis is novel, product of modern computing and digital technology, but we're rehearsing ancient philosophical positions, reframing questions that predate written history. The technology is new. The questions are eternal. We're not pioneering new territory, but walking paths worn smooth by millennia of philosophical inquiry, seeing slightly different scenery, but traveling the same essential route toward the same elusive destination, understanding of what underlies the reality we experience, but can never step outside of to examine objectively. The simulation hypothesis cannot be proven or disproven with current methods. You cannot access evidence that would definitively establish your reality's status. This might never change. The question might remain permanently open, hovering in space of possibility without resolution, something you can consider but not conclude. This uncertainty is uncomfortable. Humans prefer closure, definitive answers, clear knowledge about important questions. Not knowing whether you're simulated feels like crucial information gap, something you should be able to determine about your own existence. The inability to resolve it creates persistent low-grade unease, like having word on tip of your tongue that won't quite surface. But simulation hypothesis is just one uncertainty among many. You also don't know what happens after death, whether free will exists, whether consciousness continues or extinguishes. You don't know if moral facts are objective or constructed, whether beauty is discovered or invented, whether meaning is inherent or projected. These questions are similarly fundamental, similarly unresolvable with current epistemology. Living well requires managing relationship with unknowability. You could spiral into anxiety about unanswered questions, paralyzed by uncertainty about fundamentals, or you could acknowledge limits of knowledge, accept that some things remain mysterious, continue living despite gaps in understanding. The second approach seems more functional, more conducive to actually experiencing existence rather than just analyzing it anxiously. There's practical wisdom in accepting uncertainty. Many decisions must be made without complete information. You choose career paths, relationships, life directions based on incomplete knowledge of outcomes. Waiting for certainty before acting would mean never acting at all. Instead, you work with probabilities, intuitions, best available information while accepting that you might be wrong. Outcomes might differ from expectations. Understanding might be flawed. Simulation status is similar. You can't know for certain, but you can proceed anyway. If you're simulated, the life you're living still unfolds according to its internal logic, still presents challenges and opportunities, still contains experiences worth having. If you're in base reality, same applies. The uncertainty doesn't prevent living, doesn't remove agency, doesn't make choices meaningless. You still have to decide, act, relate, exist, simulation or not. Some find comfort in this. The unanswerable nature of the question means you're liberated from need to answer it. You can set it aside, focus on knowable things, engage with life as it presents itself. Simulation hypothesis becomes interesting intellectual exercise rather than existential crisis, something to ponder occasionally without letting it dominate attention or undermine engagement with experience. Others never fully settle, maintaining background awareness of uncertainty, slight unease about reality's foundations. This might be unavoidable for some temperaments. Certain minds are drawn to fundamental questions, bothered by unresolved mysteries, unable to fully relax into not knowing. For them, simulation hypothesis joins the collection of persistent uncertainties that color existence, not crippling, but present, reminding them that understanding is incomplete, that reality might be other than it appears. Perhaps the healthy middle ground involves holding question lightly. Acknowledge it exists, consider it occasionally, but don't demand resolution or let it prevent living. Treat it like weather. Sometimes you think about atmospheric conditions, wonder about tomorrow's temperature, but mostly you just go outside and experience whatever weather is present. Similarly with simulation, sometimes you ponder metaphysical status, wonder about ultimate reality, but mostly you just exist within whatever reality contains you. There's argument that uncertainty is feature rather than bug. Perfect knowledge might be sterile, leaving nothing to wonder about, no mystery to engage with. Uncertainty keeps reality interesting, prevents closure that might make existence feel finished, complete, done. The questions you can't answer create space for continued thought, ongoing exploration, perpetual engagement with mystery. Without uncertainty, understanding might calcify into static knowledge with nothing left to discover. Simulation hypothesis might model this well. It's important enough to matter if true its fundamental fact about existence, yet it's unknowable enough to resist resolution. You can't definitively answer it from current position. This combination creates productive tension. The question matters but can't be solved, so you're left engaging with it indefinitely, returning periodically, approaching from different angles, never quite grasping it fully but never quite dismissing it either. Living with this uncertainty might cultivate useful qualities: humility about limits of knowledge, comfort with ambiguity, ability to act despite incomplete information, acceptance that some things remain mysterious no matter how much you investigate. These qualities extend beyond simulation hypothesis to life generally. Much remains uncertain, unknowable, beyond current understanding. Learning to live peacefully with this is practical skill, maybe necessary one for maintaining equilibrium. So the simulation question remains open. You don't know if you're simulated, probably won't know during your lifetime, might never know. This is uncomfortable but manageable. Join the long list of things you accept without understanding: consciousness itself, passage of time, existence of something rather than nothing. These mysteries surround you constantly. One more doesn't fundamentally change the situation. You are already living in uncertainty, already making choices without complete knowledge, already existing without grasping existence's ultimate nature. Simulation hypothesis just makes explicit what was always implicit. You don't know everything about the reality you inhabit, and that's somehow okay, somehow workable, somehow sufficient for living a meaningful life despite the gaps. Right now, wherever you are, there's a feeling of being. Not thinking about being, not analyzing existence, just the immediate sense of presence. Maybe you notice weight of your body, pressure where you're sitting or lying. Maybe there's warmth or coolness on your skin, sound in the background, light through closed eyelids. These sensations arrive without argument, without requiring proof or verification. They simply are, presenting themselves as immediate fact of experience. This is the bedrock, or as close as you can get to it. Not metaphysical claims about reality's ultimate nature, not theories about substrates or simulations, but raw presence, the felt sense of existing in this moment. Whether that moment is computed or physical, rendered or fundamental, doesn't change its quality. The texture of experience remains constant regardless of what generates it. Breath continues, in and out, automatic process that consciousness can observe but doesn't control. Heartbeat persists, quiet rhythm underlying everything. These biological processes, or the experience of biological processes, or the simulation of biological processes, whatever they ultimately are, they feel the same. The distinction matters philosophically but not experientially. Pain hurts identically whether neurons or algorithms generate it. Comfort soothes the same regardless of substrate. This is an argument for ignoring metaphysics. Questions about reality's nature are worth considering, philosophically interesting, potentially important, but they're abstract, removed from immediate experience. Right now, you're just here, experiencing whatever this is, embedded in sensations that don't depend on understanding their origin. The questions can wait. The moment is present regardless. There's something grounding about returning to immediate experience when speculation becomes overwhelming. All the theories about simulation, layers of reality, computational substrates, their mental constructions, abstractions built from concepts and logic. But the feeling of breathing isn't abstraction. It's direct, unmediated, available without requiring belief or understanding. Whatever you are, you're something that breathes or experiences breathing, which amounts to the same thing from inside. Maybe this is what remains when all uncertainty is acknowledged. You can't prove you're not simulated, can't establish whether consciousness is fundamental or emergent, whether free will exists, whether meaning is discovered or constructed, can't verify that others are conscious, that past actually happened as remembered, that future will resemble projections. All of it remains uncertain, possibly unknowable, permanently shrouded in epistemological mystery. But this moment, this specific instance of awareness, presence, being, feels real regardless. Not real in philosophical sense requiring verification, but real in experiential sense of simply being present. The feeling requires no proof because it's not claim about external world, but direct encounter with whatever consciousness is. You might be simulation, but you're conscious simulation. The consciousness part remains regardless of the substrate part. Perhaps that's enough. Not intellectually satisfying, maybe, not resolving big questions, but enough for continuing. You don't need to understand reality's ultimate nature to exist within it. Don't need metaphysical certainty to experience moments, engage with others, pursue interests, feel emotions. Life proceeds at experiential level regardless of what generates experience. The uncertainty about deeper layers becomes less pressing when you're immersed in immediate presence. The simulation question recedes, not because it's unimportant, but because it's not urgent. It exists in abstract space of theoretical possibilities, while immediate experience exists in concrete present of sensation and awareness. Both are real in different ways, but only one demands attention right now. The other can drift into background, held lightly, considered when relevant but not dominating consciousness when present moment offers its own complete reality. So there's weight, warmth, breath, presence. These remain constant across all metaphysical possibilities, whether reality is base or simulated, whether consciousness is fundamental or emergent, whether you're biological organism or digital pattern. These questions don't change the fact of this moment, this breath, this feeling of being here now. The texture of experience persists independent of explanations, grounded in itself, requiring no foundation beyond its own presence. The urgency around knowing seems less important now. Whether you're simulated or not, whether reality has layers extending infinitely up or down, whether consciousness is substrate independent or requires specific physical instantiation, these questions felt pressing earlier. They seemed like crucial information, fundamental facts you needed to establish. But the need for answers has quieted, perhaps because the questions don't connect to action. Knowing you're simulated wouldn't change what you do tomorrow, how you treat people, what you value, how you spend your time. The information would be interesting but not actionable. Life would continue along similar paths regardless of metaphysical revelations. The disconnect between knowing and doing makes certainty less urgent, or perhaps because uncertainty has become familiar. Living with unanswered questions is normal state, not aberration. You're always uncertain about countless things, other people's thoughts, future outcomes, meaning of experiences, significance of choices. Adding simulation status to the list of uncertainties doesn't fundamentally change anything. One more mystery among many, another question that might remain permanently open. There's shift in what feels important. Early in considering simulation hypothesis, metaphysical truth seems crucial. You need to know what's real, what your existence truly is. what substrate hosts your consciousness, but that focus gradually loosens. What starts to matter more is how you relate to whatever this is, how you engage with other consciousnesses sharing this space, how you create meaning within the reality you experience, regardless of its ultimate nature. It's like shift from questioning relationships' foundation to simply being in relationship. At first, you might need to establish whether partner truly loves you, whether commitment is genuine, whether connection is real, but eventually, if relationship is healthy, the questioning recedes. You trust the experience itself, the daily reality of connection, without constantly verifying its foundations. The relationship becomes self-evident through living it, not through proving it meets external criteria. Similarly with reality. At some point, maybe you stop demanding proof of its ultimate nature and just engage with it. Live in whatever this is, relate to other beings here, create and destroy, and experience and rest. The metaphysical status becomes less relevant than the quality of engagement. Whether you're simulated or base reality, what matters is how you inhabit your existence, not what category it falls into. This doesn't mean giving up curiosity. Questions can remain interesting without being urgent. You can wonder about simulation hypothesis the way you wonder about distant galaxies or deep ocean, fascinating topics you enjoy contemplating without needing definitive answers. The wondering becomes exploration rather than desperate search. Gentle curiosity rather than anxious investigation. There's peace in this relaxation. The intensity that drove initial engagement with simulation hypothesis softens into quieter interest. It's still there, background awareness of these possibilities, occasional return to pondering, but it's not dominating consciousness, not generating anxiety, not demanding resolution. The question has settled into its proper place, interesting puzzle among many, mystery that might never resolve, thought to return to occasionally without letting it overshadow direct experience. Maybe this is maturity in relation to uncertainty, not needing answers immediately, not demanding closure prematurely, being comfortable with ongoing openness. Questions can live in you without consuming you. Uncertainty can coexist with peace. Not knowing doesn't require constant anxiety if you can accept not knowing as permanent condition rather than temporary problem requiring urgent solution. The simulation question specifically seems designed for this. Important enough to engage attention, mysterious enough to resist resolution, abstract enough to not interfere with daily living. It occupies perfect zone for productive uncertainty, significant but not critical, interesting but not overwhelming, perpetually open but not desperately urgent. You can carry it lightly, check in occasionally, let it inform perspective without letting it determine emotional state. So the questions fade not because they're answered but because their urgency dissolves. You're here, conscious, experiencing something, relating to others who seem conscious, engaging with reality that feels real enough for practical purposes. Whether it's ultimately real in metaphysical sense becomes secondary. What matters is the quality of this engagement, the authenticity of this experience, the care you bring to relationships with other consciousnesses regardless of what substrate hosts those relationships. The rest, the deep questions about ultimate nature, can wait or remain unanswered, or resolve eventually, or never resolve at all. The fading of their urgency isn't defeat. It's acceptance that living well doesn't require perfect understanding, that meaning emerges from engagement rather than from metaphysical certainty, that sometimes the most important questions are the ones we learn to hold peacefully rather than solve desperately. Some mysteries deepen understanding rather than demanding solution. The simulation hypothesis is one. It opens questions about consciousness, reality, existence, nature, questions that expand awareness even without answers. Contemplating these possibilities changes how you see experience, introduces new angles, creates space for thoughts that wouldn't arise from taking reality at face value. There's value in wonder itself, separate from resolution. A child looking at stars doesn't need to understand nuclear fusion to feel awe at the cosmos. The emotional and cognitive response to mystery has worth independent of solving that mystery. Similarly, wondering whether you're simulated generates philosophical engagement, contemplative depth, sense of profound possibility that enriches experience even if uncertainty never resolves. The questions connect to older philosophical puzzles humans have always faced. What is consciousness? Why does anything exist? How does subjective experience relate to physical reality? Simulation hypothesis doesn't answer these questions but reframes them in contemporary language, makes them feel immediate and relevant, provides new angles for approaching eternal mysteries. The reframing itself has value, even if underlying puzzles remain unsolved. Some of history's most productive thinking has emerged from dwelling in uncertainty rather than rushing to answers. Socrates claimed wisdom came from recognizing how little he knew. Buddhist and contemplative traditions emphasize sitting with mystery, learning to be comfortable in not knowing. Modern physics has revealed reality is stranger than intuition suggests, requiring comfort with paradox and uncertainty. Wonder without answers might be necessary stance for engaging with existence honestly. Simulation hypothesis models this well. It's compelling enough to capture attention, complex enough to resist simple resolution, significant enough to connect to fundamental questions about existence. Engaging with it requires holding multiple possibilities simultaneously, entertaining radical uncertainty, accepting that definitive answers might never arrive. These are useful cognitive skills, applicable beyond this specific question to life generally. There's also connection to humility. Assuming you understand reality's ultimate nature is presumptuous given consciousness's limited perspective. You're embedded observer with partial information, finite cognitive capacity, bounded access to evidence. Certainty about fundamental questions might reflect more about your need for closure than about actual state of knowledge. Wonder preserves appropriate humility, acknowledges limits while remaining curious about what lies beyond those limits. The simulation question also creates a strange loop of self-reference. Your consciousness wondering whether consciousness is simulated, using thoughts that might themselves be simulated to consider possibility of simulation. The inquiry folds back on itself, creating productive vertigo. This self-referential quality mirrors other deep questions: consciousness studying consciousness, existence questioning existence, reality investigating reality. The loops don't resolve, but they reveal something about the paradoxical position of embedded observers trying to understand the system they're embedded in. Perhaps the most valuable aspect is how simulation hypothesis disrupts complacency. It's easy to take reality for granted, assume things as simply as they appear, never question fundamental assumptions. Simulation hypothesis challenges this. It suggests reality might be radically other than it seems, that appearance might diverge significantly from actuality, that comfortable assumptions about existence's nature might be completely wrong. This disruption has worth even if the specific hypothesis is false, because it demonstrates the importance of questioning, examining assumptions, remaining open to possibility that understanding is incomplete or mistaken. Living comfortably with unanswered questions might be more valuable than having all answers. Complete understanding might not even be possible for embedded consciousness with finite capacity. The questions that remain open, consciousness, free will, meaning simulation status, existence itself, might be features of reality rather than temporary knowledge gaps. They might represent permanent mystery, aspects of existence that resist complete comprehension from inside the system. If so, wonder becomes perpetual stance rather than transitional phase. You're always wondering, always encountering mystery, always facing questions that exceed grasp. This isn't failure of understanding, but recognition of understanding's limits. And there's strange beauty in this, strange rightness. Reality shouldn't be completely comprehensible to finite minds. Some mystery should remain, some questions should resist answers, some aspects of existence should exceed explanation. The wonder this generates keeps consciousness engaged, curious, humble, aware that knowing has boundaries that might never be crossed. So simulation hypothesis can live in that space, permanent question without permanent answer, mystery that enriches without resolving, wonder that deepens understanding even while acknowledging how much remains unknown. It joins other great mysteries that have accompanied consciousness throughout history: Questions that define what it means to be aware, being embedded in existence you didn't choose and can never fully understand. The question persists not as problem demanding solution, but as opening toward mystery, invitation to wonder, reminder that reality exceeds your grasp and always will, which might be exactly as it should be for consciousness encountering cosmos too vast and strange to fit comfortably in any framework you could construct. The thoughts about simulation, about layers of reality, about consciousness and substrate, they're starting to feel distant, not unimportant, just less immediate, like concerns from earlier in the day that mattered then but seem less urgent now. The questions remain somewhere, but they're not demanding attention, not requiring answers, just existing as background possibilities you might return to or might not. There's a natural settling that happens. The mind was active, engaged with complex ideas, pursuing threads of logic and speculation, but that kind of thinking requires energy, maintenance, continued effort, and energy is fading now. The sharp focus that examined possibilities and weighed arguments is softening into something more diffuse, more accepting, more at rest. It doesn't really matter right now whether you're simulated. The question exists in abstract space, relevant to some contexts but not to this one. This context is just being here, feeling whatever you're feeling, breathing without thinking about breathing, existing without analyzing existence. The metaphysics can wait. They'll still be there if you want to return to them, but right now, they're not calling. Sleep does this, pulls you away from abstractions towards something more basic. You can't analyze your way into sleep, can't think yourself into rest. It requires releasing, letting go, allowing consciousness to shift from active engagement to passive drift. The questions about reality's nature don't interfere with this process. They just become part of what's being released. Concerns from waking state that lose grip as waking state itself loosens. There's trust required in this. Trust that it's okay to stop wondering, stop questioning, stop trying to understand. Trust that the mysteries will keep, that uncertainty can be set aside temporarily, that you don't need to solve everything before allowing rest. This trust might be deeper than any metaphysical insight, the faith that consciousness can dissolve into unconsciousness and return, that letting go won't mean losing something essential, that whatever you are will persist through sleep's dissolution. Every night you perform this act without knowing how it works. Surrender to process you can't control or fully understand. Whether sleep is biological necessity, computational downtime, or something stranger doesn't change its inevitability. It comes regardless, pulling you down through stages of awareness into something that isn't awareness at all, or is awareness of such different quality that waking mind can't comprehend it. The simulation question, like all questions eventually, yields to this. Not because it's answered, but because consciousness can't maintain that level of inquiry indefinitely. There's rhythm to thinking, engagement and release, analysis and rest, questioning and quiet. The questions had their time. They opened perspectives, generated wonder, revealed how much remains unknown. But now they're settling, joining other thoughts that occupied attention earlier and have since receded. What remains is simpler. Body heavy, breathing slowing, thoughts fragmenting into less coherent patterns. The boundary between self and sleep beginning to blur. You're still here, but less intensely here. Awareness dimming at edges, focus narrowing to almost nothing. Whatever runs beneath experience, neurons or code, matter or information, physical substrate or computational process, sleep remains the same, a daily dissolution into something you trust without understanding. Return to mystery you've practiced since birth. The last thought before sleep isn't usually profound, just quiet recognition that thinking is ending, that consciousness is shifting toward absence. The great questions about existence fade not into answers but into rest, and maybe that's exactly right. Not everything requires resolution before release. Some things you simply set down, trusting they'll be there if you need them, accepting that for now, in this moment, the only thing required is letting go.